Something happened on the morning of December 11th that no one expected. Just after passing Mars, 3I Atlas suddenly blew off half its tail. For hours, the comet's ion stream distorted, split apart, and then vanished, like a ribbon caught in a solar storm. But then came something even stranger. Telescopes began detecting a fluctuation not in the comet, but in the Sun. What followed was a cascade of data that no model predicted, and now scientists are asking one question they can't shake. If 3I Atlas is just a comet, why does the Sun look hurt? Stay with me. This isn't science fiction, it's solar physics being rewritten in real time. 3I Atlas reached a critical point in its outbound trajectory, crossing the orbital path of Mars. This moment, by all conventional models, should have been routine. The object had already passed its perihelion weeks earlier, survived an intense encounter with the Sun, and was now coasting outward. By this stage, its activity should have been waning. The comet's tail, mostly composed of ions and volatile gases, should have thinned. Instead, astronomers witnessed something no one had predicted: a sudden fracture in its ion tail. It began with a visual anomaly captured almost simultaneously by telescopes in Arizona, Chile, and the Canary Islands. What had been a smooth, continuous stream of charged particles suddenly split in two. Not gradually, not like a comet fading or shedding material over time. This was abrupt, like a fault line snapping in space. The separation was sharp, jagged, and long. A disconnection event in the language of heliophysics, but one that didn't follow the usual script. To understand the significance, it helps to know how a comet's tail forms. As a comet approaches the Sun, solar radiation and the solar wind ionize gases from the surface. These ions get swept away, forming a tail that always points away from the Sun. That tail can stretch millions of kilometers, and it typically evolves slowly as the comet moves. But what occurred with 3I Atlas was not a gentle transformation. It was a rupture. The tail fracture was recorded across multiple wavelengths. In visible light, it appeared as a sudden bend, a kink in the tail structure. In ultraviolet, the structure behind the nucleus showed a gap, an actual absence of material where there had previously been a flow. But the most telling data came from radio and spectral imaging. Instruments detected a change in ion density that was both abrupt and uneven. On one side of the fracture, the tail was still present, thin, wispy and dispersing. On the other, it was gone entirely, as though something had sliced through it, leaving one half adrift. This wasn't a minor event. It was a large-scale structural collapse of the tail's architecture. Theories began circulating quickly. Could it have been a solar wind anomaly, a collision with another object, a transient electromagnetic pulse? None fit cleanly. Solar wind at that moment had been relatively steady. No solar flare had erupted in the preceding hour, and no known object was close enough to interfere with the comet's path. The scale of the disconnection was equally puzzling. Based on time delay measurements between observatories, scientists estimate the break extended for tens of thousands of kilometers in just under 15 minutes. That kind of structural shift is not typical of passive outgassing. It looked mechanical, it looked intentional. Even more confusing was what didn't happen. The core of the comet remained completely unaffected. Its brightness remained stable. Its trajectory showed no wobble. If the tail had broken due to internal stress or instability in the nucleus, some change in the object's rotation or mass loss would have been expected. There was none. The separation looked clean, too clean, like a system shutting off a function it no longer needed. For observers watching in real time, the scene was surreal. A massive interstellar object had just shed a major component of its structure without any warning or obvious physical trigger, and yet it did so without losing stability. The comet kept moving, unfazed, as if nothing had happened. The moment 3I Atlas crossed the orbit of Mars, something else crossed a line too. Our understanding of what this object is. A comet doesn't typically choose to discard part of itself, but on that morning, that's exactly what it looked like. And in the minutes that followed, the story got even stranger. In the hours following the tail fracture of 3I Atlas, something unexpected happened in the solar wind. As the interstellar object moved steadily outward past the orbit of Mars, solar observatories began to notice an invisible ripple spreading through the heliosphere. Not a visible flare or a magnetic storm, but a density wave, subtle yet real, and it moved with surgical precision. Scientists would later call it a shock line, and its timing couldn't have been more perfect. The solar wind is a continuous stream of charged particles, mostly electrons and protons, flowing out from the sun in all directions. It's chaotic, turbulent, and influenced by everything from sunspots to coronal mass ejections. Normally, when an object like a comet travels through it, the interaction is predictable. The object creates a disturbance in the stream, but it's mild and irregular, similar to how a rock disturbs water. But what happened on December 11th wasn't mild, and it wasn't irregular. At approximately 6:40 UTC, the Parker Solar Probe, then in its outbound arc past the Sun, detected a sudden spike in particle density. The probe had been monitoring a relatively calm patch of solar space, with smooth magnetic field lines and a steady flux. Then, without warning, a compression wave passed through, a sharp, compact front of elevated plasma pressure. The magnetic field twisted, the particle count doubled briefly, and the solar wind slowed just enough to register across multiple instruments. Within minutes, that same ripple was picked up by ESA's solar orbiter, positioned further out along the ecliptic. What caught scientists off guard was not just the presence of the shock, but its direction. It was moving away from the Sun, but not as part of a solar event. It traced back to a singular point in space, the position of 3I Atlas. There had been no flare, no coronal mass ejection, no change in solar activity to justify such a pulse. And yet, there it was. A crisp pressure line moving in perfect alignment with the comet's path, as though it had been cast outward from the object itself. The data raised immediate red flags. A shock line implies a momentary interruption in plasma flow, a region of space where the pressure increases sharply, forcing particles to compress, bounce, or redirect. In most cases, this happens when solar material hits something dense, like a planet's magnetosphere or a spacecraft hull. But 3I Atlas has no magnetosphere. It has no magnetic shielding, no thick atmosphere, and no known surface field strength strong enough to generate that kind of resistance. Which led to a question that has not yet been fully answered. What did the solar wind hit? Some scientists proposed that the tail fracture had released a sheet of highly charged particles, an expanding cloud dense enough to cause momentary compression. But that wouldn't explain the clean profile of the wave. Others suggested the object had discharged something, ionized gas or plasma, that acted like a reflective surface. But again, the data didn't show a lingering field or halo. The most provocative idea came from a small team at the Max Planck Institute. Using simulation models, they proposed that the shape and material of 3I Atlas might have temporarily created a conductive cavity in space, a kind of floating shield, not magnetic but reactive to solar plasma. If the object had shed a reflective layer, perhaps the fractured tail was more than just a trail. It could have created a microbubble in the solar wind. And as that bubble collapsed, it would have triggered the shock line seen by the probes. That theory, while still speculative, fits the timeline. The tail fracture happened first, the density spike followed within minutes, and the shock line moved not from the Sun but outward, like a pulse responding to loss. What this all means is still unclear. But one thing is certain. On December 11th, the solar wind recorded an impact with something it didn't expect. Not a planet, not a flare. Something else, travelling in perfect silence and shedding pieces of itself like signals. While telescopes on Earth were still analysing the aftermath of 3I Atlas's tail fracture, a separate observation from deep space sent shockwaves through the astrophysics community. At approximately 07:02 UTC on December 11th, a brief but unmistakable bright flash was recorded by the European Space Agency's solar orbiter. It appeared in ultraviolet imaging for less than 5 seconds. But what stood out wasn't its duration, it was the location. The flash originated precisely at the coordinates where 3I Atlas was travelling, just beyond the orbit of Mars. At first, the data was flagged as a potential sensor glitch. Spaceborne observatories like the Solar Orbiter regularly experience cosmic interference, radiation spikes, thermal artifacts, even brief misreads caused by high-energy particles. But this flash didn't behave like an error. It followed the shape of a real object. It had gradient, structure. It moved slightly with the object's own trajectory. ESA scientists reran the calibration routines. They checked for solar flares, particle events, and internal software hiccups. Nothing abnormal was found. More importantly, two other instruments, onboard spectrography and heliospheric imagers, captured matching anomalies within seconds of each other. The ultraviolet flash was no phantom, it was real, and it was centered on 3I Atlas. In the images, the flash appears as a sharp, irregular burst, a small, radiant bloom erupting from the side of the object. Not from the tail, not from solar backscatter, but from the nucleus zone itself. It wasn't round, it wasn't diffuse like reflected sunlight. It was shaped, lopsided, layered, almost like a geometric flare. The radiance emerged from one point and expanded outward in an uneven halo before vanishing into the surrounding void. The flash happened so quickly that no follow-up image captured its evolution. But data from the imaging array showed an important detail. The flash preceded a minor shift in solar plasma density, measured moments later by Parker's solar probe. That order matters. It means the event didn't result from an external solar interaction. Instead, it initiated something. Something the solar wind then responded to. Speculation grew quickly. Could the flash have been a volcanic-style outburst? A sudden venting of highly pressurized material from deep within the object? That would be rare, but not impossible for a volatile-rich body. Yet if that were the case, spectrometers should have recorded spikes in carbon monoxide, carbon dioxide, or hydroxyl emissions. But the spectrum following the flash went flat. There were no chemicals, no gas, no particulate trail, just a burst of light. That absence became the story. One possibility raised quietly in internal reports was electroluminescence, a brief emission of visible light caused by a high-voltage discharge. It's been seen before in Earth-based plasma experiments and atmospheric events like lightning, but never in a comet. For that to occur, the comet would need to hold charge potential and release it as a sudden arc. In the vacuum of space, that scenario becomes even more exotic. Could 3I Atlas have contained internal charge storage? Could the tail fracture have destabilized a field that then discharged through the surface? That theory remains speculative. But ESA's own polarization logs support it. For several minutes before the flash, the object showed anomalous reflection angles, as if its surface alignment was shifting unnaturally. A few degrees at first, then more, and then the flash. Almost like a realignment followed by ignition. The most unnerving hypothesis suggested by one analyst was simple. The flash wasn't an accident. It was a response, a trigger, a result of the tail detachment perhaps. A brief energetic signal, visible, intentional, and timed. Whatever it was, ESA's bright flash is now a central feature in the timeline of December 11th. It wasn't a comet crumbling. It wasn't solar light bouncing off ice. It was something else, brief, bright, and decisive. And it marked the beginning of a deeper shift in how we would view this object. Not just as a visitor from another star, but as a presence capable of reacting. While all eyes were focused on 3I Atlas and the strange flash caught by ESA, something else was quietly unfolding at the heart of our solar system. On December 11th, one of the Sun's most active regions, AR 3513, was entering a volatile phase. Solar astronomers had been tracking it for days. It was large, magnetically twisted, and showing signs of instability. Multiple solar observatories had predicted a jet event. But when the coronal jets finally fired, something about their trajectory stopped scientists in their tracks. The Sun had missed. Typically, solar jets, narrow focused bursts of superheated plasma, erupt along magnetic field lines and follow precise arcs through the heliosphere. Their direction is governed by magnetic loops, not aim, and yet on December 11th 2 separate jets ejected from AR 3513 curved sharply, away from the expected angle. Not toward Earth, not toward any other body of interest, but laterally, as if something in the magnetic field had been deflected or distorted. At first, the deviation seemed minor, a few degrees at most. But when the Solar Dynamics Observatory overlaid the projection against prior models, the mismatch became impossible to ignore. The magnetic lines had warped, not from within, but from influence outside the solar surface. The field looked like it had buckled around an invisible boundary, and the timing, precisely aligned with the tail fracture and flash event from 3I Atlas. To be clear, the Sun doesn't typically target anything. its emissions follow magnetic structures shaped by internal plasma motion. When jets misalign, it's usually due to rotational timing, subsurface shifts, or simple miscalculations. But this time, those explanations didn't hold. The solar models had been accurate. AR3513 had behaved as expected, until the exact moment that 3I Atlas destabilized its own tail structure just beyond Mars's orbit. The question emerged, did something between the Sun and 3I Atlas redirect the solar jets? Or even more unsettling, did the presence of 3I Atlas alter the Sun's local field geometry? ESA's solar orbiter contributed additional data. Its onboard heliospheric imager caught a faint bending in plasma density lines. Again, only on the side facing 3I Atlas. For roughly 20 minutes after the jets fired, the local solar wind stream showed lateral drift. A slow, unnatural push outward, like a curtain being dragged. These deviations matched none of the recorded solar phenomena. No flare, no CME, no collapsing loop. Some theorized a temporary flux rope, a cylindrical twist of magnetic fields that had somehow formed in space between the comet and the Sun. But there was no known mechanism for a comet to generate one, especially from that distance. Others proposed that the tail separation from 3I Atlas had discharged material with unusually high conductivity, causing localized interference in the heliospheric current sheet. Still, those ideas didn't fully explain the shape of the jets or the sudden distortion of magnetic field lines on the Sun itself. One solar physicist posed a question no one wanted to answer. What if the jets missed because they were pushed, not by wind, not by mass, but by influence, as if something temporarily altered the electromagnetic architecture of the Sun's surface? The Sun, of course, is not aware, but its field is responsive, and whatever happened on December 11th made the Sun react like a living organism, adjusting to unexpected pressure. The jets that should have followed their arc didn't. The paths they should have taken curled outward and weakened. The energy that should have reached its intended velocity dispersed, and somewhere along that bent trajectory, billions of kilometers from the Sun's surface, was a lone interstellar object, now missing its tail, now pulsing with silence. What had it done? Or maybe more accurately, what had it just absorbed? By mid-morning on December 11th, what had started as a curious anomaly, the sudden fracture of 3I Atlas's tail, was beginning to look like a piece of something much larger. The timeline was the key. One event followed another with uncanny precision. The tail fractured. A bright flash occurred at the comet's core, the solar wind reacted, and then, just when the system should have begun to settle, the Sun flared. The flare wasn't massive. In solar terms, it barely registered as an M-class event, but it was surgical in its timing. It erupted from AR3513, the same magnetic region that had just fired off misaligned solar jets. The flare began at 7:06 UTC, exactly 4 minutes after the tail rupture, and when scientists from NASA and ESA began overlaying the heliophysical data with 3I Atlas's own trajectory, something became unmistakable. The flare vector pointed directly toward the region of space where 3I Atlas had just ejected half its tail. Normally solar flares are random. They follow cycles, yes, and tend to emerge from known active regions, but their precise timing and target are unpredictable. They don't aim. They don't synchronize. But this flare behaved differently. It aligned. It fired off not randomly into space, but along a clean angular path. The same angular path where the tail disconnection event had just occurred. Solar physicists reviewing the telemetry noticed another disturbing pattern. The flare wasn't preceded by the usual chaotic build-up. Most flares rise from a storm of magnetic tension. Field lines twist, sunspots churn, and pressure builds over time. But AR3513 had been stable for hours. Its last emission had been nearly 20 hours prior. The region wasn't supposed to erupt again for at least another day. Until it did. One model, produced by researchers at the University of Colorado's Space Weather Team, ran a simulation of the magnetic flux near the time of the flare. When they introduced a hypothetical plasma void, a zone where charged material had suddenly been removed from the interplanetary medium, the flare's behavior matched perfectly. And that's exactly what the 3I Atlas tail loss had created. A sudden vacuum of ionized mass, freshly stripped from the comet and adrift in solar wind. But it wasn't just the flare's direction or the plasma hole, it was the sequence that disturbed analysts the most. 0658 UTC, tail disconnection occurs 07-2. UTC, bright flash detected at 3I Atlas's core, 7 UTC, compression shock recorded in solar wind, 7 UTC, solar flare erupts from AR 3, 9. UTC, ultraviolet imaging shows field line distortion, 5 events, 11 minutes, and all of them anchored to one object that shouldn't even be active anymore. The idea that a comet, interstellar or not, could somehow trigger a solar flare sounds absurd at first. The mass difference is staggering. The Sun is 330,000 times more massive than Earth. A comet's influence, even with a volatile tail, is like a grain of dust trying to move a mountain. But some began to ask, what if the comet didn't cause the flare, but coordinated with it? Theories began to emerge. Could the tail loss have discharged enough charge to collapse local plasma gradients and, in turn, destabilize solar magnetic fields? Could the object have released conductive particles that catalyzed field line reconnection? Could the comet's own internal structure have been engineered in such a way that it stores, amplifies, or redistributes energy collected from solar pressure? Or, in the simplest terms, did the comet know the flare was coming? Some physicists remain skeptical. The data is strange, yes, but they caution against assigning agency. Yet others point to the precision of the flare, the symmetry of the event sequence, and the clean, deliberate nature of the tail disconnection. It's not just that the flare happened, it's when it happened. And in astrophysics, timing is everything. Just minutes after the flare aligned with the fractured comet tail, something unexpected began to appear in the light. Not the kind of light you can see with the naked eye, but polarized light. Filtered, oriented, and structured. It was subtle at first, a gentle curve in the angle of solar reflection. Then, over the course of 20 minutes, the data sharpened. Instruments across 3 observatories recorded the same result. The polarization signature around 3I Atlas had flipped. In astrophysics, polarization is one of the most revealing yet least understood tools. It measures how light scatters off surfaces, be they dust clouds, comet tails, or planetary atmospheres. When sunlight reflects off a rough, uneven surface like ice or dust, it scatters chaotically. The polarization signal tends to be low or diffuse. But when that light reflects off something smooth, metallic, or geometrically consistent, the signal becomes directional, structured, and when it flips, that usually means the surface orientation has changed dramatically, or the nature of the surface itself has shifted. On the morning of December 11th, the European Space Agency's polarimetric imager began detecting a deepening in the polarization trough around 3I Atlas. Where the expected pattern should have dipped gently below zero and then returned as the object rotated, this dip became abrupt and reversed. The polarization vector, instead of remaining negative, which is typical for cometary dust scattering sunlight at small phase angles, suddenly turned positive and stayed there longer than expected. This is incredibly rare. Only a handful of comets have ever shown this behavior, and none of them were interstellar. To the trained eye, this meant one thing: a smooth specular reflection had emerged on the comet's surface. In plain terms, it started reflecting light like a mirror. But comets don't act like mirrors. They're rough, porous, and chaotic. Their surfaces scatter light like fog, diffuse and messy. A polarization flip of this kind suggests something reflective, structured, and aligned has either become exposed or activated. As analysts dug deeper, they realized something even more bizarre. The flip coincided exactly with the flare burst from AR 3. The Sun had emitted a focused pulse. Seconds later, 3I Atlas's polarization signature changed, and not just in one band. Across ultraviolet, visible, and near-infrared spectrums, the same flip was detected. One team in Japan running simulations proposed a chilling possibility. The object had altered its surface characteristics in real time, rotating, shifting, or unfolding something that changed its optical properties. They weren't the only ones thinking that way. Back at the Max Planck Institute, polarization experts looked at the data and noted that the signal's inversion angle, the point where negative becomes positive, had narrowed significantly. That only happens when the scattering surface becomes more uniform. In technical terms, the object had gone from behaving like a dusty snowball to something closer to a polished, elongated panel. Had the object rotated a structured surface into view? Had the tail loss exposed something beneath the outer layer, a shield, a plate, or a segment built to catch light and redirect it? If true, it wouldn't be the first time a strange interstellar object had shown anomalous polarization. The first, Oumuamua, displayed weak signs of it back in 2017, but nothing this dramatic, and certainly nothing timed with solar events. By late morning on December 11th, researchers began referring to the change informally as the mirror phase. A comet that had lost half its tail survived a synchronized solar flare and now was reflecting sunlight as if it had just switched modes. Skeptics pointed to exotic ice or dust properties. Maybe carbon-rich material had become exposed. Maybe there was a crystallized shell hidden under the surface, but that wouldn't explain the clean vector change, or why it happened just after the tail separated. When polarization flips, it tells a story. And in this case, the story 3i Atlas was telling was that it had just revealed a new face. By mid-morning on December 11th, radio telescopes tracking 3i Atlas began reporting something they hadn't seen before. The object's Doppler profiles were breaking down. These profiles, which are normally used to measure the velocity of particles being ejected from the comet, began to distort. Then they vanished altogether. What should have been a steady stream of measurable motion dissolved into static. The signal collapsed. To understand what that means, we have to look at how Doppler spectroscopy works in space. When gas and dust escape a comet, especially one exposed to sunlight, those particles move at high speed, sometimes several kilometers per second. As they fly away, they scatter light, and that light shifts slightly, depending on whether the particles are moving toward or away from us. That shift, called the Doppler effect, allows scientists to chart the shape, speed, and behavior of the tail. In an active comet, these profiles are crisp. You'll see peaks for water vapor, carbon dioxide, and dust at different speeds. They rise and fall over time, reflecting jets firing, particles dispersing, or solar wind compression. Even during disruptions like tail fractures, Doppler profiles tend to spike, not disappear. But 3i Atlas did something else entirely. At around 07:18 UTC, just minutes after the polarization flip, facilities in Chile and Hawaii began reporting inconsistent data from the ion tail. Then, the Green Bank telescope confirmed what they were seeing. The signal wasn't weakening gradually, it was collapsing, all at once. Every velocity profile, from hydroxyl radicals to carbon monoxide lines, lost coherence. The system that had been tracking particle speed from the tail for weeks suddenly showed nothing but noise. The tail hadn't just detached, it had gone silent. This puzzled analysts deeply. In a natural comet, even if a tail segment detaches, the drifting material continues to emit measurable radiation for hours or even days. Dust doesn't just vanish. Ions don't stop moving. If anything, the breakup of structure should have resulted in more signal, not less. Theories poured in. Perhaps the ejected tail had become so diffuse that it dropped below detection threshold. But that would require dispersion speeds 10 times higher than those observed. Others suggested interference from the sun's recent flare might have overwhelmed the signal, but no nearby comets showed similar distortions. The flare had passed, and other solar system bodies remained readable. Then came a third idea, and it wasn't easy to ignore. What if the tail wasn't dispersing naturally, but being reabsorbed or neutralized? This concept, though rare, has precedent in laboratory plasma physics. Under certain electromagnetic conditions, a charge stream can be neutralized by encountering a region of opposing charge or density. In other words, the comet might have crossed an invisible boundary of interference, a place where particle velocity and signature get flattened, erased from detection. That possibility grew more compelling when Japan's Nobuyama Radio Observatory detected a faint, wideband flattening of signal to noise in the same region. Not only was there no Doppler signal, there was also no thermal noise from the missing tail. It hadn't just stopped emitting, it had stopped interacting with space entirely. Whatever the cause, the implications were serious. The Doppler profiles weren't just silent, they had been cut off, like a live feed suddenly terminated, and they remained offline for nearly 3 hours. During that time, 3i Atlas maintained its trajectory, brightness, and reflective signature. but the expelled particles, the ones we'd expected to trail behind it like breadcrumbs, were simply gone. The collapse of Doppler data marked another turning point in the mystery, because if the object wasn't ejecting anything anymore, then maybe, just maybe, it never needed to. Scientists scrambled to make sense of the collapsed Doppler profiles, yet another anomaly appeared, this time visible to both amateur and professional astronomers. At precisely ear-weight for UTC on December 11th, observers across 3 continents captured something that shouldn't have existed. A briefly formed anti-tail on 3i Atlas. Not a simulated illusion, not a processing glitch, a real structured spike of material that appeared to stretch backward, toward the sun. In comet science, anti-tails are known phenomena, but they're exceedingly rare and require very specific viewing conditions. Usually an anti-tail is a trick of geometry. Earth crosses the orbital plane of the comet and, for a short time, we look directly into a flat sheet of older dust particles that have spread out ahead of the comet in its orbit. From our perspective, it appears as if the tail is pointing the wrong way, toward the sun, rather than away from it. But 3e. Atlas's anti-tail wasn't an illusion. It wasn't a planar effect or a product of orbital geometry. It was seen from multiple positions on Earth with different viewing angles. Even more perplexing, it wasn't made of dust, it was ionized. Using narrowband filters tuned to sodium and hydroxyl emissions, researchers confirmed the spike was composed of freshly emitted material, not legacy dust from a past orbital pass. And it wasn't spread out in a fan, it was focused, narrow, dense, and aligned directly with the solar vector. This completely breaks with what we know about comet behavior. Solar radiation and solar wind push ion tails directly away from the sun. That's Comet Physics 101. Material simply doesn't move sunward without external force, and yet, for nearly 36 minutes, 3i Atlas was ejecting something that did. ESA's solar orbiter managed to catch a partial view of the anomaly. Their heliospheric imager recorded a filament of bright plasma trailing inward, not diffusing, not bending, but accelerating sunward in a near-straight line. Then, as suddenly as it appeared, the anti-tail collapsed, fading completely by 0841 UTC. No comet on record has produced a sun-facing jet of this nature, especially not one made of ionized gas. The only remotely comparable phenomenon is a sunward-pointing jet observed in comet Encke in 2007, but that was driven by extreme solar wind shearing during a coronal mass ejection, not by the comet itself. In the case of 3i Atlas, the solar environment had been quiet for nearly an hour. There was no flare, no CME, and no shockwave to explain a forced reversal. So what caused the anti-tail? Some proposed a sudden inward-facing collapse of a magnetic field structure within the comet's own coma. If the object carried any localized charge, or had recently lost a significant structural component, like, say, half of its tail, then the resulting shift might have created a temporary magneto-hydrodynamic channel. That could, in theory, guide charged material inward briefly before the field collapses, but this is highly speculative, and it's a mechanism never observed outside controlled plasma labs on Earth. Others, more cautiously, began to whisper the possibility of directed mass ejection. In other words, thrust, not random venting, not passive chemistry. A sunward release of material designed to generate backward momentum, a maneuver straight out of propulsion science. This interpretation gained weight when researchers noticed a slight shift in the object's radial velocity immediately after the anti-tail vanished. The comet's motion didn't deviate much, but the direction of its reflective vector changed by a measurable fraction of a degree, like something had nudged it. Whatever the anti-tail was, it didn't act like an accident. It behaved like a system, brief, controlled, and purposeful. And in the silence that followed, the object's environment returned to normal, but no one who saw that sun-facing stream of particles forgot what it looked like. A comet doesn't aim at the sun. But for 36 minutes on December 11th, 3i Atlas did. Just when it seemed the sequence of anomalies around 3i Atlas couldn't become more layered, the object's visual brightness surged, suddenly, sharply, and without any natural reason. This surge came after the tail fracture, after the polarization flip, and immediately following the collapse of the brief anti-tail that had pointed unnaturally toward the sun. At 0845 UTC, ground-based observers began reporting that the comet had increased in visual magnitude by nearly an entire order. Amateur astronomers in Italy, Chile, and South Africa all noticed the same thing within minutes of each other. They were observing in clear skies, using mid-range aperture telescopes, and what they saw didn't require deep data processing. The comet had simply brightened, visibly and unmistakably. This wasn't a flare, not in the traditional cometary sense. A flare usually results from volatile ices sublimating rapidly and emitting gas and dust in a burst. When that happens, we see an increase in coma size, a diffused outer glow, and a broadening of the visible profile. But with 3I Atlas, there was no coma growth, no expanding halo, no measurable outgassing increase. Instead, the object's core became brighter, sharper. It concentrated light rather than dispersing it. For observers tracking the change, it was as though the nucleus had polished itself mid-flight. The Hubble Space Telescope wasn't in a position to view the object at the time of the surge, but data from the Pan-STARRS Observatory in Hawaii, which was sweeping the region in preparation for a separate tracking session, caught the object just minutes after the peak. The comet had stabilized, its brightness holding steady, no longer climbing. It was as though whatever had just happened had completed a cycle and settled. The event raised two immediate questions. First, what had caused the brightness to spike so dramatically, without any evidence of thermal or volatile activity? Second, why had the brightness not decayed, as would be expected after a transient flare-up? Under normal physics, an interstellar object travelling away from the Sun at this stage should be dimming, its reflective surface area should be reducing as dust disperses, the solar flux acting on it is declining. In simpler terms, it should be fading out of view. But 3I Atlas was not obeying those rules. When polarization data from earlier that morning was cross-referenced with brightness readings, a clear correlation emerged. The surge began moments after the anti-tail collapsed, and exactly as the polarization vector stabilized in its flipped state. This indicated that the object's surface had become more uniformly reflective, and it had done so in seconds. Spectral data from the same period showed an unusually flat albedo curve, consistent with specular reflection, not diffuse emission. That is, it wasn't glowing, it was reflecting, cleanly, precisely, and efficiently. This kind of behavior suggests a geometrically smooth surface, not a chaotic rocky nucleus covered in regolith and vapor vents. Several researchers quietly suggested what many were thinking. The object had entered a new phase, a new state, one where the tail was no longer needed, where outgassing had ceased, and where the remaining structure was optimized for visibility, not for decay. Could it be that the tail had simply been a shield, a temporary surface layer now discarded? Could the surge in brightness be the result of that outer layer shedding to reveal something more efficient beneath? There is no proof of this. But the timing, once again, was unignorable. The anti-tail vanished, the polarization stabilized, the brightness surged, and then nothing changed. No drop, no fade, just a calm, constant brightness. 3. Atlas was no longer behaving like a dying comet. It was behaving like an object that had finished transforming, and now it simply held its glow, like something ready. While ground-based observers tracked the strange stability of 3I Atlas's new brightness, space weather monitors positioned near the edge of the heliosphere began to detect something even more puzzling. A magnetic curl forming not near the comet, but in the outer heliopause itself. The heliopause is the invisible boundary where the sun's solar wind slows down and yields to the interstellar medium. It's far beyond the planets, closer to the limits of our solar bubble than any spacecraft has fully crossed. Usually activity there is slow, gentle gradients in magnetic pressure, ripples from solar storms that take months to arrive. But on the morning of December 11th, the pattern changed. The Voyager 1 spacecraft, still transmitting from deep interstellar space, picked up a sudden curling distortion in the interstellar magnetic field just beyond the heliopause. Meanwhile, instruments aboard NASA's Interstellar Boundary Explorer, IBEX, and data from the newer IMAP mission, both studying solar wind interactions at the solar boundary, independently logged a twist, an unexpected spiral compression forming in the magnetic sheath that envelops our solar system. At first, this seemed unrelated to 3I Atlas. After all, the comet was nowhere near the heliopause. It was travelling through the inner solar system, But the data told a different story. Time-stamped sequences showed that the curl began forming at the exact same time the antitail collapsed and the Doppler profiles vanished. Not before, not after, during. The synchrony was too tight to ignore. Magnetic curls in space aren't random. They often result from complex pressure gradients, especially when magnetic fields meet opposing forces. Think of it like a fluid vortex, except instead of water, it's magnetism bending against a change in external current or field structure. For a curl to form in the heliopause, something needed to apply subtle but coherent pressure on the entire shape of the heliosphere, which raised the question, could an object within the inner solar system cause a detectable shift in the outermost shell of our heliosphere? Under standard physics, the answer is no. The Sun dominates this zone. Comets are small players, even interstellar ones. But this wasn't a typical comet, and the changes IBEX and IMAP observed weren't turbulent or chaotic. They were structured. The curl formed in a clean clockwise spiral, detectable in the energetic neutral atom, ENA, flux measurements. Normally these atoms scatter outward evenly from solar wind collisions, but now they were showing signs of being redirected inward along an invisible curve. It was like the heliopause had grown a coil, a spring-like magnetic shape, forming and holding. Some theorists began connecting this to a concept called field resonance entanglement, a phenomenon in which moving objects with large enough plasma sheaths can interact with magnetic structures at incredible distances by triggering harmonics across charged particle flows. This theory remains fringe, but it's gaining traction among researchers studying large-scale cosmic filaments and fast-moving interstellar anomalies. If that's what happened here, it would mean 3I Atlas had somehow synchronized, magnetically and directionally, with the heliopause from more than tens of billions of kilometers away. There's no known natural mechanism for such coupling, but the coincidence in time, shape, and structure suggested influence. Not control necessarily, but resonance, a kind of magnetic handshake. For the average viewer, nothing changed. The sky looked the same. The object still glowed, drifting silently toward Earth's orbit. But at the edge of the solar system, where the wind meets the void, the heliopause curled inward, like something out there had tugged on its skin, just a little, and the only thing that had changed in the solar system at that moment was 3I Atlas. By the late morning of December 11th, researchers were deep into analysis of what should have been a standard post-event signature: residual thermal radiation from the ejected tail segment of 3I Atlas. When a comet loses a part of its tail, especially in such a violent, abrupt manner, there should be leftover heat scattered across the region it once occupied. Dust, gases, and ices retain solar warmth. Even in the vacuum of space, particles radiate infrared light for hours, sometimes days. But 3I Atlas wasn't following any known thermodynamic behavior. Across multiple observatories, including the Infrared Telescope Facility in Hawaii, the Stratospheric Observatory for Infrared Astronomy, SOFIA, and even James Webb, the expected thermal signature of the missing tail simply wasn't there. Not faint, not distorted, gone. Infrared imaging is one of the most reliable ways to detect leftover mass in space. Even the coldest, particles glow faintly in the right bands. When a tail breaks off, the temperature differential between the particle field and the empty background of space leaves a distinct footprint. And this is especially true for dust-rich tails. Dust absorbs sunlight and re-emits that energy as thermal radiation. But every spectrum sweep conducted between 0730 and 10SD UTC showed the same thing: a black void where the tail used to be. No warmth, no emission. Not even the slightest excess signal above the cosmic background. The data was so clean it looked like the tail had never existed. That kind of thermal silence raised immediate questions. If the tail truly detached, where did all the mass go? And more importantly, how did it cool instantly? Some researchers theorized that the tail had rapidly dispersed into such a fine cloud that its individual particles no longer emitted detectable levels of infrared radiation. But that explanation broke down under scrutiny. The total surface area of a dispersed cloud should still produce a diffuse but measurable thermal field. Yet, thermal readings showed nothing, as if the tail had never been made of matter at all. Others floated the idea that the tail may have been composed of non-standard material, something that doesn't respond to solar radiation the way normal dust or ice does. But even highly reflective or inert materials, like silicates or carbon-rich particles, still radiate some heat. What if, as a few quietly suggested, the tail wasn't lost or dispersed? What if it was reclaimed? The idea was radical but disturbingly consistent with the data. If 3i Atlas had a mechanism, natural or otherwise, to absorb, recapture or neutralize its own outflow, that would explain both the disappearance and the lack of thermal residue. There would be no particles left to heat up, no surface area to emit radiation, no trace in the sky to follow. One speculative framework that entered the conversation was cryogenic folding, a theoretical process in which ejected materials are restructured into a compact configuration and cooled rapidly using internal heat sinks or passive radiation manipulation. Such a concept exists in advanced spacecraft shielding models, but has never been applied to natural bodies. Still, this possibility explained the timing. The anti-tail collapsed, the Doppler signals vanished, and shortly after, the infrared ghost of the tail, expected and prepared for, never showed up. The systems were ready to receive something, but what they received was silence. From a storytelling perspective, the eerie part wasn't just the missing heat, it was the intelligent feel of the sequence, as though the tail had served its purpose and then ceased to exist on command. It wasn't blown off, it was dismissed, and in its place, no radiation, no dust, no warmth, just the cold, hard stillness of interplanetary space, unmarked, untouched, and emptied. As the day continued and instruments stabilized across the network of global and orbital observatories, researchers began noticing another disturbance, one that wasn't as explosive as the tail fracture, nor as eerie as the thermal silence, but perhaps even more significant. The jet vectors of 3i Atlas, the directional emissions of material from its nucleus, had begun to reorient, but not outward as expected. Instead, they were shifting toward the sun. At first glance, this looked like an observational error. Comets vent volatile gases and dust when heated by sunlight, and those jets always trail behind or at perpendicular angles to the solar vector, depending on the rotation and structure of the nucleus. It's a simple equation. Sunlight hits, ice sublimates, gas escapes outward and away from the sun due to pressure and thermal acceleration. That's Comet Dynamics 101. But the spectral data and high-resolution imagery told a different story. What had once been multi-directional jets, some radiating laterally, others curving backward, were now narrowing into streamlined sunward-facing lines, as though the object had turned its thrusters around. 3 independent observatories confirmed the change. First was the Very Large Telescope in Chile, which noticed a faint shift in vector angles using polarized imaging at sunrise. Then came a confirmation from Lick Observatory in California, using spectroscopic velocity mapping. Finally, the SOHO spacecraft registered a faint forward emission of charged particles within its coronagraph field of view, particles that were accelerating toward the solar center line. This development contradicted the most basic laws of outgassing and solar dynamics. What made the observation even more disturbing was that this wasn't the first time 3i Atlas had defied this principle. Earlier, during the brief anti-tail event, a directional flow of particles had moved sunward, but it was written off as a rare and likely one-time alignment artifact. Now, the object was showing persistent forward vectoring, not one jet, multiple, and they were coordinated. If natural sublimation was the cause, we would expect randomness. Jets firing wherever surface ices are exposed, reacting to sunlight in chaotic bursts. But the new configuration was geometric, linear, symmetrical. The jets appeared to realign as if following an internal axis. This suggested either a complete restructuring of the object's internal heat distribution, somehow rerouting gas flow intentionally through specific surface vents, or an artificial process, governing where and how thrust is produced. Some researchers speculated that we might be witnessing rotational vector stabilization, a theoretical maneuver used in deep space propulsion to reorient a body by using limited mass ejection for directional correction. In spacecraft, this is done through controlled nozzles and spin mapping. In natural comets, this is unheard of. And yet, here was 3i Atlas, shedding mass toward the very star that was supposed to be, pushing it away. The deeper implications were subtle but massive. If an object can use its own internal forces to push toward the sun, it's not following passive orbital mechanics. It's adjusting, realigning, responding, or it's aiming. This realization led to a storm of quiet discussion among specialists in orbital dynamics and astrophysical fluid mechanics. Could 3I Atlas be realigning its trajectory using sublimation as controlled thrust? Could the Sun be more than just a heat source for it, possibly even a destination? Whatever the motive, one thing was now clear. 3I Atlas wasn't simply venting anymore, it was steering. Following the abrupt reorientation of the jet vectors toward the Sun, attention quickly turned to the light signature 3I Atlas was giving off. Every known object in space emits or reflects light in a way that can be broken down into a spectral profile, a fingerprint of its composition, surface features, and thermal properties. These signatures help us understand what something is made of, how it behaves, and how it interacts with the forces around it. But on December 11th, a different pattern began to emerge. As global telescopes focused on the object for deeper analysis, a strange trend became clear. The spectrum of 3I Atlas was flattening. Normally, a comet's spectrum includes sharp peaks and valleys, known as emission and absorption lines, caused by the reflection and release of specific elements like carbon, hydrogen, sodium, or water vapor. These features tell scientists exactly what's being released and in what amounts. But 3I Atlas was now losing those lines, not gradually fading, but flattening out into a smooth, featureless curve. At first, researchers thought it was an instrument calibration error. Could something have been interfering with the spectrometers? Were the tracking systems being thrown off by solar interference or atmospheric distortion? But then the pattern was verified, again and again, from multiple observatories and spacecraft platforms, all using independent systems. It wasn't the tools, it was the object. Over the course of 2 hours, the once complex spectral signature of 3I Atlas began to resemble what physicists call a blackbody curve, a smooth, idealized thermal emission that lacks the fine structure typically seen in natural objects. This kind of curve is usually observed in stars or heated metals under controlled lab conditions, not in fragmented cometary bodies from another star system. More unsettling was the timing of the change. The flattening began just after the jets reoriented, and while the brightness remained stable, the color profile started shifting subtly toward the infrared, while losing all traces of previously observed materials like carbon monoxide and silicate dust. There were no emission spikes, no absorption gaps, just one smooth arc, quiet even, and unnatural. What does it mean when a comet suddenly starts behaving like a perfect radiator? It means that it's no longer reflecting or emitting light due to chaotic surface reactions. It means that its surface has either become uniform, or that what we're seeing is no longer a true surface at all. It could be a shell, a smooth structure, or some kind of energy-controlled field regulating how light is emitted. Scientists watching this transformation debated whether the surface itself had changed. Had the ejection of the tail revealed a core with entirely different optical properties? Or had the object's surface undergone a rapid reconfiguration, melting, folding, or restructuring into something new? Some of the most experienced astrophysicists pointed out that spectral flattening of this kind has never been observed in comets. Not in Oumuamua, not in Borisov, not in Hale-Bopp, Encke, or Hyakutake. It is not part of any known comet life cycle. In fact, it's the opposite of what's expected. As a comet loses mass and nears the end of its activity cycle, its spectrum typically becomes more chaotic, more noisy, not less. It fragments, breaks down, releases more diverse materials from deeper layers. But 3I Atlas wasn't becoming more complex. It was becoming simpler, clean, sterile, controlled. It was as if the object was shedding not only its material layers, but its identity as a natural object. And the light it gave off, now featureless and calm, no longer carried the signature of chaos. It carried the signature of intention. While the spectral profile of 3I Atlas continued to flatten, removing all traces of volatile activity, a new visual anomaly emerged, a faint ring, barely perceptible at first, then gradually sharpening with each pass of optical enhancement. The detection came from the European Space Agency's solar orbiter, which had been monitoring the object from a vantage point closer to the ecliptic plane than Earth-based telescopes. At approximately 11:20 UTC on December 11th, instruments on board the orbiter captured a sequence of high-contrast images showing a perfectly circular feature forming just ahead of the main body of 3I Atlas. It was not a flare, not a tail fragment. It was a thin, radiant ring, faint but consistent, encircling the object with geometric precision. Initially dismissed as lens reflection or solar artifact, the ring persisted across multiple angles and filter settings. Infrared filters revealed no heat signature, while ultraviolet lenses showed a mild fluorescent outline, suggesting particle excitation. It wasn't glowing from within, it was reacting to solar radiation in a way that produced a smooth, coherent outline. More surprisingly, the ring wasn't stationary. It appeared to be locked in position relative to the object's spin, maintaining a fixed radius and tilt while rotating slowly, as if tethered by magnetic or gravitational forces. Unlike natural gas halos or coma expansions, both of which tend to be irregular and diffuse, this ring was sharply defined. Even the spacing from the core remained stable across observations. The ESA team cross-checked with instruments aboard Gaia and Bepi Colombo, both of which also picked up subtle anomalies in local particle flow consistent with the presence of a structure, not just a gas cloud. Data hinted at electrostatic repulsion or plasma confinement forming a boundary around the object, something that could, in theory, create a visible ring under the right conditions. Theories emerged fast. Some compared it to shepherd moon dynamics, like those seen in Saturn's rings, where small orbiting bodies maintain ring integrity through gravitational nudging. Others suggested centrifugal ejector trapping, where material spins off and stabilizes in orbit due to momentum and field effects. But the truth was, this didn't behave like any natural ring system. It had no debris field, no clumping, and no expansion drift. The particles, if that's what they were, stayed in perfect alignment, not colliding or dispersing. There was no sign of fragmentation, and no visible mass exchange between the ring and the object. In fact, some imaging even suggested the ring may not be made of matter at all, but of a light distortion itself. A few radical voices inside the ESA began to whisper about frame lensing, a theoretical phenomenon in which localized space-time curvature bends light around a point, forming a ring-like illusion. While highly speculative, the idea wasn't without precedent. Einstein rings caused by gravitational lensing can form around black holes or distant galaxies, but this was different, closer, controlled, and if 3I Atlas was somehow bending light around itself, then this wasn't just a comet anymore. More conservative theories held the line. Maybe it was a dust ring, maybe a temporary emission belt formed during the tail ejection event. But the problem remained. The shape was too perfect, too cold, too quiet. As the hours passed, the ring didn't fade. It became more defined. It matched the spectral flattening. It rotated in harmony with the jet alignment, and it signaled, to those watching carefully, that 3I Atlas had entered a new phase, one not of decay, but of construction. Whatever had blown off its tail had cleared the way for something else to form, and now that thing was circling it, flawless, still, and glowing faintly in the sun's light. In the late afternoon of December 11th, the Hubble Space Telescope was cleared for a new series of high-resolution exposures targeting the central mass of 3I Atlas. With the sudden appearance of a ring-like structure and the flattening of its spectrum already causing a quiet stir within scientific circles, there was one goal in mind: resolve the nucleus, pin it down. See what's left at the heart of this object. What Hubble returned, however, wasn't what anyone expected. Instead of capturing a bright, icy core, what most assumed would be the residual nucleus of a comet stripped of its tail, Hubble caught a shadow, not cast, by the object onto space, but within the object itself. It appeared in the raw data as a small, ultra-dark central void, a region of dramatically reduced reflectivity and light return that defied normal exposure compensation. No matter how the contrast was adjusted or how filters were layered, the center of 3I Atlas refused to resolve. The perimeter of the body showed faint gradients of scattered light, especially around the edges where the jet activity had been previously observed. But in the middle? Nothing. A black disk. Cold. Empty. Opaque. This was not a silhouette. It wasn't the shadow cast by an external light source. It was a non-reflective region embedded within the object, as though light was entering but not coming back out. At first, image analysts at STSCI thought the shadow might be a sensor artifact or an internal reflection flaw in the imaging array. But alternate wavelengths confirmed the same pattern. Near-infrared, ultraviolet, polarized light all showed a consistent, unmoving central void. Some called it a cavity, others said absorption zone. A few, more cautious voices called it a blind spot, a term borrowed from optics, not astronomy. But the implications quickly turned serious. If the center of 3i Atlas was no longer scattering or emitting light in any wavelength, that meant it had changed at a structural level. A comet's core, even when shrouded by dust or gas, still reflects some light, whether by surface granularity, mineral content, or residual activity. But this was perfect darkness, and unlike black holes or neutron stars, this object lacked the gravitational pull to trap light. It wasn't heavy enough, it wasn't massive. So what then was causing the optical suppression? Several theories were proposed within hours. The first suggested that the core might have collapsed inward after the tail ejection, forming a dense cluster of non-reflective material, perhaps a carbon-rich shell that had cooled and hardened, blocking outgoing light. But this didn't match the thermal maps. There was no infrared heat to suggest compaction or stress. Another theory pointed to field distortion, a highly theoretical concept in which magnetic or electrical fields interfere with incoming and outgoing photons, causing localized invisibility zones. This is sometimes simulated in plasma research labs, but has never been seen in nature at this scale. Then came a more chilling possibility, that this wasn't a physical shadow at all, but a deliberate cloaking field masking the interior from observation, a kind of optical silence designed to hide something at the center of 3i Atlas. The silence surrounding this idea was telling. It wasn't outright rejected, it wasn't dismissed, it was simply not discussed in official summaries. Instead, the public-facing briefings referred to the core as anomalously non-reflective and requiring further study, but off-record among the tight circles of deep space physicists and spectral imaging teams, the term core shadow stuck. Because that's exactly what it looked like, a flat, round, unwavering patch of darkness where light refused to go, and if that shadow wasn't a side effect, it might very well be the objective. As the chaos of the tail separation settled into silence, attention turned not just to what 3i Atlas had become, but to what it had left behind. Following the moment when the object blew off nearly half its tail, multiple observatories expected the debris cloud to behave like any natural ejection, dispersing into solar orbit, gradually breaking apart and interacting with sunlight, radiation, and solar wind in predictable ways. But instead of the expected noisy aftermath, a strange pattern emerged. There was nothing. No signal. No detectable radio reflection from the tail debris. Normally, comet fragments and outgassed material continue to reflect and scatter radio waves, especially at longer wavelengths used by deep space radar and Doppler mapping arrays. Even the smallest icy particles, with the right density and orientation, can bounce back detectable pings, especially when scanned from high-gain radar installations like those at Arecibo's successor platforms or NASA's Deep Space Network. But when those radar arrays focused on the trail of 3i Atlas's ejected mass, now drifting slowly behind it in a curved spiral, what came back was a void. No bounce, no echo, no distortion, no phase delay. It was as if the particles had become invisible to radio. At first, this was written off as interference. December 11th was an active solar day, with bursts of ionospheric noise in certain bands. But after rerouting through clear windows and coordinating global pings across Europe, South America, and the Lunar Pathfinder array, the results were the same: radio silence. This wasn't atmospheric, it was deliberate absence. And that raised an urgent question. Where did the debris go? Optically, high-powered scopes could still spot a diffuse cloud of particulate matter spreading out in a shallow arc. It looked like dust. It shimmered faintly. But it didn't reflect light the way water ice or silicate grains normally would. And most disturbingly, it refused to interact electromagnetically. No radar signature, no microwave scatter, no L-band or X-band return. It simply absorbed the signal, as if it had been coated or replaced. One group of atmospheric physicists noted similarities to stealth materials used in aerospace design, where the surface is engineered to scatter incoming waves away from the source, or absorb them entirely. Such materials are complex to produce, requiring microscopic structural engineering. But now those same qualities were being observed in a cloud of comet fragments floating in space. That's when the second anomaly was noticed. The debris wasn't decelerating. Usually after an ejection, fragments slow down, especially as they spread out and begin to feel the pull of solar gravity and the pressure of solar radiation. But 3I Atlas's tail debris held formation unnaturally well. Its arc remained coherent, as if locked in a mild gravitational tether or guided by field lines. It did not drift as dust clouds normally do. It hovered, and it listened to nothing. This behavior defied decades of known comet tail dynamics. More than just silent, it was ghost-like, present to optical systems but absent from the electromagnetic spectrum. A few researchers suggested that we may not be looking at debris at all, but something else, a shell, a veil, or perhaps a decoy. What if the ejection wasn't the result of an internal rupture or structural fracture, but a distraction? What if the tail wasn't lost, but shed on purpose? A discarded outer layer that served a mission, thermal shielding, visual camouflage, even mass balancing, and now that purpose was complete. And what remained behind was engineered not to respond, not to reflect, not to reveal. A silent field drifting behind a now shadowed core. And in that silence, radio telescopes caught their first undeniable confirmation of intent. Because in space, noise is natural, silence is engineered. As the fragments of 3I Atlas's ejected tail drifted quietly behind it, observatories across the globe turned their attention back to the object itself, searching for signs of ongoing activity. Historically, comets remain active long after tail events, with outgassing, the sublimation of volatile ices, continuing as sunlight penetrates deeper layers. But with 3I Atlas, something far stranger happened. Outgassing fell to zero, not gradually, not in slow decline. It stopped, suddenly and completely, just hours after the tail separated. This was first noticed by the team operating the submillimeter array in Hawaii, who had been tracking molecular emissions like carbon monoxide, cyanide, and formaldehyde, typical traces that spike when a comet is exposed to solar heat. These molecules are usually the fingerprints of internal activity, leaking from vents or fissures as sunlight strikes the surface. But their instruments, tuned to pick up even the faintest signal, detected nothing, literally nothing. The same silence was confirmed by ALMA in Chile and IRAM in Spain. Across every radio frequency where outgassing signatures should have appeared, the lines were flat. There was no ammonia, no methanol, no water vapor, not even the faint whiffs of dust ions that usually rise from a body as it stabilizes. The outgassing had gone dark. This was unprecedented for an object this close to the Sun. Even inert asteroids exhibit some level of degassing when subjected to this much solar radiation. Trapped materials slowly release from fractures, leaving a fingerprint in the surrounding space. But 3I Atlas, after ejecting its tail, had become completely sealed. To some scientists, this pointed to a rapid crust formation. Perhaps the tail loss had revealed a molten layer that cooled and hardened quickly, forming a thick shell that blocked further activity. But thermal readings didn't support this. The surface wasn't cooler. It was still warm enough to drive sublimation, if sublimation were still possible. Others began whispering about a more radical possibility, that the material beneath the surface was no longer volatile at all, that it had either been used up, or that it had never been natural to begin with, because what was now emerging was not just a dormant rock, but something that appeared deliberately inert, an object that had transitioned from a dynamic emitter to a perfectly quiet body, immune to the sun's touch. Even more curious was the optical behavior. With no gas coma, the body should have dimmed. But 3I Atlas retained a steady visual magnitude, with no fading, no haze, and no distortion. It was as if the coma had not been shut down, but retracted. This was reinforced by spectropolarimetric readings from the Sofia Aircraft Observatory, which showed a total collapse of light scatter from surrounding particles. The halo was gone. The body remained. And what remained was sealed. Quiet, reflective, but no longer reactive. A few researchers suggested that we might be witnessing the final phase of an artificial shedding process, a purge of unnecessary outer mass, followed by structural lockdown. If this were a vessel, a probe, or even a decoy, this would be the point at which it had revealed its true self. A core that doesn't emit, a body that doesn't vent, an engine, or casing, that no longer breathes. And this is where the word comet began to vanish from private research notes. Because comets don't just stop outgassing, they fade, they fracture, they flail, but 3i Atlas had done none of that. It had closed, it had shut off, it had chosen silence. And in that unnatural stillness, it seemed to be preparing for whatever came next. By the evening of December 11th, a quiet shift was underway at multiple NASA observatories. Analysts and researchers, poring over data from the Deep Space Network, SOHO, Hubble and JWST, were no longer framing 3i Atlas's behavior as a typical cometary event. Instead, behind closed doors, the terminology began to change. Not ruptured, not broken apart, not even fractured, but disengaged. The word first appeared in a secure message thread between mission analysts at NASA Goddard and JPL, summarizing the tail loss incident that occurred over Mars' orbital path. The conclusion, calmly and clinically stated, was unnerving. It didn't fragment, it disengaged. This was not a physical failure, it was a sequence. The tail, which had appeared dense, vibrant, and full of ionized emissions only hours prior, had cleanly separated from the object in what now resembled a controlled detachment. The velocity gradient across the tail debris was uniform. The angle of separation was symmetrical. There was no rotational tumble, no thermal irregularity, and no visible stress signature on the main body of 3i Atlas. To any trained aerospace analyst, this was not a break. It was a procedure. Several engineers from the Mars Reconnaissance Orbiter team, who had experience modelling mechanical deployment systems, were called in to examine the motion patterns of the departing material. Their response? The behaviour of the ejected mass mirrored a stage release, the kind used in multi-phase spacecraft or orbital vehicles shedding external fuel tanks, and once that comparison was drawn, more questions followed. Why would a comet execute a release manoeuvre? Why would the detachment be so uniform, so balanced, so clean? More importantly, what was left behind? This wasn't just an inert rock coasting through space. The body that remained was still producing symmetric jet vectors, still holding course with tight precision, and now operating without any visible trace of natural cometary behaviour. It had lost the volatile layers, it had stopped outgassing, it had masked its core, and now, in the absence of debris, it was perfectly operational. That phrase, perfectly operational, was not said out loud in the public briefings, but it appeared in a preliminary internal summary forwarded to the Office of Planetary Defense. Under the section marked Trajectory Integrity, the object was described as retaining flight stabilization post-disengagement. In plainer terms, it's still flying like it's meant to. Unlike fragmented comets, which tend to spiral out of control after shedding mass, 3i Atlas remained locked on a steady vector. There was no drift, no angular change. It had simply detached and continued, lighter, quieter, and somehow more precise. Even more disconcerting was the absence of chaos. Natural fragmentation events tend to create unpredictable signatures, rogue particles, chaotic spins, delayed bursts of sublimation. But this detachment event was calm, silent, geometrically sound, as if it had been timed. NASA's analysts stopped trying to model it with comet templates. Instead, they began referencing mechanical comparisons, satellite jettison protocols, capsule release models, modular probe staging events, and quietly, some of them began to say what no one dared include in a press release. This wasn't a breakup, it was a systems command. It didn't explode, it didn't crack, it let go. And now, with half its mass behind it, and a sealed core ahead, 3i Atlas was no longer behaving like an object reacting to the sun. It was behaving like something that had completed a phase and was entering the next. Just as the scientific community began adjusting to the idea that 3i Atlas had disengaged rather than broken apart, the sun responded, not with a typical flare or coronal mass ejection, but with something far more unexpected. At precisely 14 hours after the tail detachment, solar observatories recorded the release of a spiral-shaped jet erupting from the sun's equatorial region. Unlike the violent, chaotic ejections typically seen during periods of heightened solar activity, this event unfolded with eerie symmetry. The jet did not arc chaotically into space. Instead, it unfurled in a spiral, as though unwinding from a central point. The structure was not turbulent, it was precise. Thin bands of plasma twirled outward like a coil, maintaining geometric integrity as they extended into the solar system. First spotted by the Solar Dynamics Observatory (SDO), the spiral jet appeared as a glowing helix, twisting its way out of the photosphere and reaching into the heliosphere like a corkscrew. This wasn't just beautiful, it was uncharted. Solar jets are known to be linear or fan-shaped, driven by sudden magnetic reconnection events, but a spiral jet implies a rotational force, an origin point spinning fast enough to twist the escaping plasma into a corkscrewed filament. Within hours, the SOHO spacecraft confirmed the spiral wasn't dissipating. It held form for several million kilometers, subtly rotating as it pushed outward. Its structure was visible across multiple bands from ultraviolet to X-ray, and at no point did it fragment or veer. It behaved like a thread pulled tight, stretching between the Sun and something else. That something else was 3I Atlas. Its position, on the trailing edge of Mars' orbit, placed it almost directly downstream from the jet's trajectory. The alignment wasn't exact, but it was close enough to raise alarm. Solar physicists began to question whether the spiral jet had been triggered. After all, the timing was suspicious. Less than a day earlier, 3I Atlas had blown off its tail and sealed its surface. Now the Sun was emitting a coiled stream of charged plasma, unlike anything seen in recent years, on a vector loosely pointed at the object's path. Some propose that the spiral jet was a coincidental magnetic anomaly, possibly a complex form of flux rope formation that simply hadn't been captured this cleanly before. But others argued the timing and shape were too precise. The key clue came from the Solar Terrestrial Relations Observatory, STEREO-A, which captured magnetic field models of the jet's path. Instead of diffusing over distance like most ejections, the spiral remained focused, its magnetic vectors converging into a tight stream even after travelling millions of kilometres. One analyst described it as a guided stream of solar breath, and 3I Atlas, strangely, showed no reaction. Its trajectory remained unchanged. No thermal bloom, no jetting, no deviation. It was as if the object either absorbed the stream, ignored it, or anticipated it. There was no fragmentation, flare-back, no shroud of dust kicked up by impact. Whatever hit it, if anything did, it passed like wind around stone. And that raised a darker question. What if the spiral jet wasn't meant to hit 3I Atlas, but to reach it? A connection attempt, a signal. Because, while comets react to solar events, melting, flaring, rotating, this one had done none of those things. Instead, it had silenced itself, then watched. And the Sun, in an act unlike any in its documented recent behaviour, had emitted something not explosive, but elegant, structured, directed, and for the first time it wasn't clear which of the two, the comet or the star, had initiated contact. As the spiral jet from the Sun slowly dissipated into space, instruments recalibrated and eyes returned to 3I Atlas. But what came next only deepened the mystery. The object, silent, sealed, and no longer outgassing, was not dimming. It was brightening. This puzzled even the most seasoned astrophysicists. Without a tail, without a coma, and without reflective ice grains swirling around it, 3I Atlas should have faded. By every model of cometary behaviour, the energy input from the Sun had dropped below the threshold needed to maintain its luminosity. There were no more gas emissions, no more volatile surface activity. Yet optical sensors across the James Webb Space Telescope, pan-stars, and even amateur observatories reported a consistent uptick in reflected brightness. The numbers didn't make sense. That's when the term re-emerged in NASA's internal briefings, energy budget violation. This wasn't the first time it had been whispered. Months earlier, during its approach to Jupiter, 3I Atlas had already displayed signs of internal thermal retention inconsistent with a natural body. At the time, those anomalies were brushed aside, attributed to shielding effects or surface albedo errors. But now, with the tail gone, the coma vanished, and no solar-facing outgassing, there was nowhere for the anomaly to hide. The math was simple. The amount of solar radiation hitting the surface was insufficient to account for the visible energy being emitted. The object was, once again, glowing more than it should. This phenomenon had been seen before, in brief, unexplained flashes from near-Earth objects, or short bursts during meteoric entries, but never in a sustained, controlled form like this. The brightness held steady for over 4 hours. One theory suggested a latent heat release. Perhaps internal pockets of pressurized material had opened slowly and were radiating thermal energy. But there were no thermal signatures, no emission spectra, and no acoustic signatures from interior cracks or vents. Another proposed explanation involved optical manipulation, a surface coating or geometry capable of amplifying reflected light in narrow bands. This would suggest an advanced structure designed to control visibility across wavelengths, something not seen in nature, but common in stealth and illumination technologies. Yet, for all the speculation, one fact dominated the reports. 3i Atlas was emitting more light than it should be able to absorb or reflect, and that meant energy was coming from somewhere else. Several labs, including a group at MIT's Haystack Observatory, ran recalculations using photon pressure differentials and gravitational lensing variables. None could resolve the discrepancy without introducing a second energy source, either internal or external. Which begged the question, was it powering itself? This wasn't a question of propulsion. 3i Atlas's trajectory remained clean, steady, and unaccelerated. But it was a question of intentional illumination. Why glow now? Why stay visible after the tail, the coma, and the noise had been stripped away? In one classified NASA document, an analyst posed a quiet possibility. If the object has entered a phase of passive observation, this luminosity could be a form of signal, or calibration, a light meant to be seen, or a beacon. The term energy budget violation stopped being treated as a math error. It became a marker, the signature of something operating on non-natural principles. Not in the sense of breaking physics, but of following a logic that Earth's current physics couldn't yet model, because this wasn't an explosion, it wasn't a thermal spike, it was a controlled increase in visible magnitude, smooth, consistent, and unforced, and when it plateaued, just before reaching its brightest, it stopped, like a switch flipped off, stable again, silent again, no more light than expected, but no less than needed to remind us, it's still there, and it knows what it's doing. For weeks the inner core of 3i Atlas had remained hidden, obscured first by a dense coma, then by erratic tail structures, and finally by the object's own silence. But with the tail gone, outgassing halted, and brightness stabilized, astronomers finally had a clear, uninterrupted view of the body itself. What they saw next was not what they expected. The core wasn't round. Data captured from the James Webb Space Telescope and confirmed by high-resolution stacked imagery from multiple Earth-based observatories revealed something no comet had ever shown with such clarity. The nucleus of 3i Atlas appeared elongated, not spherical. At first, this was dismissed as an optical illusion, a trick of angle or shadow. But as images came in across various spectrums and the object rotated slowly across its solar approach, a consistent outline began to form. It wasn't irregular or lumpy, it was precisely shaped, a narrow stretched form with clear linear edges and a tapered end. Some described it as spindle-like, others compared it to a flattened cylinder. But none could deny the symmetry. Natural cometary nuclei are chaotic. Even Oumuamua, which stunned the world with its cigar-like appearance, never showed clean surfaces or consistent geometry. 3i Atlas was different. Its elongation was too clean, too centered, and too deliberate to ignore. Infrared readings showed even thermal distribution across the entire length of the core. There were no hotspots, no surface vents, no craters or indentations that suggested erosion or sublimation. The surface was smooth, unbroken, and, most notably, non-rotating in the usual chaotic sense. It wasn't tumbling like a rock. It was gliding, maintaining a slow, stable, axial alignment as if controlled. Even more fascinating was the reflectivity differential across its surface. The tapered ends reflected slightly less light than the central region, almost as if designed for directional masking. This created what one analyst called a visibility gradient, a property unheard of in naturally formed bodies. And yet, for all the strangeness, it wasn't the shape alone that alarmed researchers. it was what the shape suggested, because elongated cores are not efficient for natural stability. They precess, they tumble, they fracture, unless they're being stabilized on purpose. Theories began to swirl behind the scenes. Could 3I Atlas's core be a housing structure, the protective casing of something inside? Could the elongation serve a functional purpose, like shielding, signal beaming, or directional energy absorption? The question wasn't what it looked like. It was why it looked that way at this moment in its journey. The object had just discarded its tail. It had silenced all emissions. It had entered what appeared to be a dormant cruise state, and now, in full view, it had revealed a shape that simply didn't fit any known cometary classification. NASA analysts flagged this development as highly atypical. The European Space Agency's Near-Earth Object Coordination Center published a short bulletin using more cautious language, referring to the structure as an uncommonly shaped nucleus. But among off-record briefings, a new term had started to spread: structure positive. In mission speak, it meant the object showed more indicators of intentional design than natural formation. The elongation wasn't proof, but it was a signal, quiet, cold, and waiting. Because now that its tail was gone and its jets were still, what was left behind wasn't a dying rock. It was a core, stretched, symmetrical, and steady. And for the first time since 3I Atlas appeared, it no longer resembled a comet at all. It looked like a vehicle, one that had shed everything unnecessary, and now hovered in full exposure, its form finally speaking for itself. With the elongated core now exposed and the brightness plateauing across all optical bands, analysts turned their focus to one particular measurement: albedo, or surface reflectivity. It was supposed to be a mundane step in confirming what the object was made of. Instead, it became the final break in the natural theory. As light readings poured in from James Webb, Pan-STARRS, and several ground-based infrared observatories, a clear pattern emerged. The surface of 3I Atlas was bouncing back more light than any known comet. Far more. Calculations showed that over 90% of the incoming sunlight was being reflected. That number wasn't just high, it was impossible for a natural body in this region of space. To put that into perspective, fresh snow on Earth reflects about 80 to 85% of light. A young, icy moon like Enceladus reflects slightly more. Even polished metals under laboratory conditions rarely reflect above 90% of the full spectrum. But this was something else entirely, and yet it wasn't uniform. Scans revealed that reflectivity varied slightly across different bands, favouring specific wavelengths. In the visible light range, the object's surface reflectivity peaked. In the infrared range, it dropped sharply, almost as if the surface was tuned to be seen only under certain observational conditions. In other words, it wanted to be seen, but only just enough. Reflectivity this high suggests a deliberately engineered surface, something polished, smoothed, and possibly treated to manipulate visibility across a spectrum. There were no signs of dust, debris, or natural frost layering the object. This wasn't chaotic ice. It was a pristine, light-controlling skin. A senior optics engineer at ESA described the readings bluntly. If this was built, someone built it with the goal of managing energy, not just surviving it. Because there's more to high reflectivity than visibility. Surfaces that bounce light also reject heat. With over 90% of the sun's energy deflected, 3I Atlas was absorbing almost nothing. In space terms, it was behaving like a mirror, a near-perfect one. This mirrored quality had another effect. It masked thermal readings. Since so little energy was retained, infrared telescopes had almost no signature to lock onto. From a thermal imaging perspective, the object had become nearly invisible. Cold, featureless, perfectly silent. Some theorized that the sudden jump in reflectivity wasn't natural evolution but an activation, a shift in surface state that occurred after the tail detachment. That would suggest this wasn't just a passive body drifting in space. It was something capable of changing its external properties on command. And now, with the outer skin rejecting almost all solar input, two interpretations began to circulate. Defensive mode, designed to survive proximity to solar wind, UV radiation, or other observational attempts. Observational mode, reflecting light precisely because it was now watching, collecting, or awaiting contact. Either way, the natural comet hypothesis was deteriorating. ESA quietly updated its internal status tag on 3i Atlas from comet-like to object of interest. NASA's Jet Propulsion Laboratory stopped issuing regular updates altogether, replacing them with irregular technical memos, circulated only to high-clearance research labs and defense advisors, because once a body begins to control how much light it reflects, and when it does it, you're no longer studying a drifting rock. You're watching a decision. Reflectivity above 90% is not a feature. It's not a coincidence. It's not an accident. It's a choice. And somewhere inside that elongated core, behind that flawless mirror skin, something may still be watching us back, untouched by heat, untouched by force, untouched by time, just visible enough to let us know we were meant to see it. For months, astronomers had tracked the chemical fingerprint of 3i Atlas across every observable band. As with most interstellar objects, its spectral profile had included the usual suspects: trace amounts of carbon, oxygen, nitrogen, and a scattering of volatile organics. These readings were weak, but familiar. They placed 3i Atlas somewhere within the wide realm of natural origin, albeit on the edge of the bizarre. But then, in the early hours of December 11th, something changed. Carbon disappeared. Spectrographic scans from Mauna Kea, ESO's Very Large Telescope, and JWST all confirmed the same quiet absence. The once faint but consistent carbon absorption lines in the object's light signature were gone, not diminished, not absorbed into noise, gone. It was a ghosting event, clean and complete. Carbon is a baseline element in virtually every space body we've ever observed. From comets to asteroids, even rocky moons and exoplanet atmospheres, carbon makes itself known. It exists in multiple states: gas, dust, complex molecules, and frozen solids. Even deep space comets carry it, burned into their outer shells by eons of exposure and pressure. It's always there. So when carbon disappears from a known body without a trace, scientists don't shrug it off. They escalate. The first suspicion was a sensor error. Multiple observatories triple-checked their instruments' timing and calibration models, but the results were consistent. Carbon's signature peaks, the tiny dips and spikes in the optical and infrared spectra, were no longer present anywhere along the core's reflectance path. And the strangest part, no other elements were affected. Hydroxyl traces remained. Sodium, oxygen, magnesium, all still measurable. But carbon, the backbone of every organic structure and the building block of cometary dust, had somehow been erased from the visible scan. This opened the door to theories no one had wanted to touch. Had the carbon been removed? If so, how? Why? Removal implies activity, and activity implies choice. One working theory suggested that the carbon-rich outer layers of 3i Atlas had simply flaked off after the tail detachment, leaving behind a cleaner metallic core. But that doesn't explain the precision of the disappearance nor the timing, only hours after the object's surface reflectivity had passed 90%, and the spiral jet from the sun had brushed past its trajectory. Another proposal was more chilling. What if the carbon wasn't lost, but masked? Spectral masking is a known concept in military stealth technologies. If a surface or field can be tuned to suppress specific light signatures, it can render key elements undetectable. On Earth, we've barely begun experimenting with that kind of material science. But in space, against the raw precision of sunlight and cosmic radiation, you'd need something far more deliberate. Carbon isn't just a chemical marker, it's also a diagnostic tool. Telescopes use its spectral lines to measure age, temperature, and composition. If 3i Atlas had intentionally hidden those lines, either through surface alteration or more advanced field manipulation, it could mean one thing: it no longer wanted to be read. A shutdown of biological markers, a rejection of organic classification, or perhaps a transition into a different phase of observation. What made the disappearance even harder to explain was the lack of debris. There was no traceable dust cloud, no dispersal trail, no new absorption in surrounding space. It was as if the carbon had not left, but simply ceased to interact with light. Some scientists offered one last possibility, desperate to stay within natural theory. They called it a rotational mask. A section of the object may have rotated to hide its previous surface, exposing a new face, deeper, cleaner, perhaps metallic. But that again implies design symmetry, and the object's now visible elongation had already challenged the randomness of rotation. So the truth became harder to deny. Carbon was gone, and no one knew how or why. But if something, anything, had chosen to hide its building blocks, that meant it knew it was being watched. And if it knew that, it may have just answered back, by going dark in the one place we always look first. As 3I Atlas continued its silent drift beyond Mars's orbital track, and the silence of its missing tail deepened, attention gradually turned away from the object itself and towards something else, something much closer to the Sun. Roughly 6 hours after the spectral carbon lines vanished, a new anomaly appeared. A single bright spot, faint but unmistakable, was detected on the inner edge of the solar limb, just outside the corona. At first, it was dismissed as an imaging glitch or a solar artifact. After all, the Sun produces eruptions, flares, and bursts every day, especially during heightened magnetic activity. But this wasn't a flare. It didn't radiate out, it didn't expand, it didn't pulse. It just sat there. A clean, stable, intensely white-hot point of light, stationary, unblinking, and detached from any solar surface features. The SOHO spacecraft noticed it first during routine coronal scans using the LASCO C3 coronagraph. Then SDO, the Solar Dynamics Observatory, confirmed the anomaly at the same coordinate in extreme ultraviolet. Several Earth-based solar telescopes, including Big Bear and Kanzelhoe, reported a matching signature within the visible spectrum. Its properties didn't fit any known solar activity. Solar flares erupt with extreme magnetic violence and shift within seconds. Coronal loops arc and flicker, prominences rise slowly and collapse back into the chromosphere. But this bright spot held its shape, its intensity, and most confusingly, its location. It didn't drift along with the Sun's rotation. It hovered, fixed in place against a background that should have moved. Within 20 minutes, 2 key details raised eyebrows across every observatory tracking the Sun. First, the light was pure, a perfect spike across almost every wavelength, visible, ultraviolet, near-infrared, no flicker, no decay. Second, it was not emitting heat. Instruments measured no coronal spike from the anomaly. If it was a local reaction within the Sun's atmosphere, it should have sent shockwaves of ionization through the surrounding plasma. But the region stayed calm, no burst, no field disruption. It was light, without fire. And then the timing was noticed. The anomaly had appeared on the exact opposite vector from where 3I Atlas now drifted. If you were to draw a line from the object's current position through the Sun, the bright spot would sit almost precisely on the same axis. That axis had never mattered before, until now. What was this light? A signal? A result? A cause? No one knew. Some speculated it could be a gravitational lensing artifact, perhaps a distant background source warped by solar mass, but no background object that bright had been catalogued in that location, and gravitational lensing would have produced a curved smear or arc, not a single punctual pixel of brilliance. Others whispered more radical ideas, that the bright spot was not from behind the Sun but from within it, or that the Sun had been pierced by something so precise it didn't erupt, but simply emerged, perfectly silent, perfectly stable, and intentionally hidden on the Sun's far side from Earth-based eyes. One thread of speculation even traced the vector through 3I Atlas and suggested the object had simply sensed something. Something we were never meant to catch unless we looked exactly right, at exactly the wrong moment. The bright spot lasted just over 6 minutes. Then, as quickly as it appeared, it faded out. No flare, no burst, no wake, nothing. And just like that, the Sun returned to normal. But those 6 minutes changed everything. Because when a dying interstellar object sheds its skin, silences its tail, hides its elements, and then quietly draws a perfect line through the Sun, you don't just keep watching the object, you start watching the light, and you begin to ask, not what it is, but what it left behind. Just hours after the mysterious bright spot faded near the Sun, NASA analysts at the Jet Propulsion Laboratory issued a quiet but game-changing update. It wasn't front-page news, and it didn't come with fanfare. It came in the form of a small correction, an adjustment to 3I Atlas's rotational data tucked inside a routine orbital bulletin. But hidden inside that correction was a revelation. 3i Atlas had changed its spin, specifically its angular velocity, the rate at which the object rotates around its axis, had shifted, not just slightly, not from collision, and not from outgassing. It had shifted against all known cometary dynamics. Angular velocity in natural objects is typically one of the most stable parameters in space. It's set early in a body's formation, influenced by initial spin momentum, gravitational interactions, or physical impacts. Even when comets expel material, the result is gradual and predictable, a slow wobble, maybe a deceleration over time. But 3i Atlas broke that rule. Data showed a rapid asymmetrical adjustment, executed in a window of less than 30 minutes. The object's rotational speed increased slightly while its axis of rotation tilted away from Earth by a few measurable degrees. The shift was smooth, no chaotic tumble, no evidence of instability. In other words, it didn't spin out of control. It realigned, with precision. For days, NASA teams attempted to attribute the shift to solar wind pressure, gravitational perturbations from Jupiter, or residual torque from the detached tail, but nothing fit. Solar pressure was far too weak at that distance. Jupiter's influence had already passed weeks ago, and with the tail fully ejected and no new jets observed, there was no force left to cause rotation. Which led to one troubling conclusion: the object had altered itself. Imagine a tumbling spacecraft correcting its orientation without visible thrusters or external inputs. That's what 3i Atlas looked like, except no engines were seen, no heat signatures, no momentum loss, just a clean, deliberate change in its spatial attitude. What made it more baffling was the timing. The shift occurred shortly after the disappearance of carbon from its spectral profile, and almost simultaneously with the appearance of the bright spot near the Sun. 3 anomalies, tightly packed into a narrow window of time. 3 shifts, none of them explainable through natural means. The orientation shift also carried another implication. By changing its angle of rotation, 3i Atlas altered how it interacted with solar light, and how we observed it from Earth. Light curves suddenly changed, reflectivity patterns became skewed, thermal echo signatures became harder to read. It was as if the object had turned away, not just from Earth, but from visibility itself. Some scientists viewed the angular velocity shift as the object's final act of concealment, like a door closing slowly behind it. The tail had been dropped, the surface masked, the spectrum cleaned of the markers, and now even its rotation was no longer aligned for clear observation. Others viewed it as a pivot, a redirection, a conscious alignment towards something else in space, perhaps another object, perhaps the Sun itself. Avi Loeb, when asked to comment, simply said, "Rotation is one of the few things in the cosmos that tells us whether an object is free or guided." And with 3i Atlas, that freedom now seemed in question, because when a comet changes its spin on cue, without any visible cause at the same moment as light bends near the Sun, it stops behaving like a comet, and starts behaving like a craft, or at the very least, like something with internal rules that we've never seen before, and now it was turning away, not tumbling, not broken, just repositioning, like it knew where it wanted to go next. The change was so small it almost slipped through unnoticed. After the angular velocity shift, teams around the world continued to update 3i Atlas's orbital trajectory, expecting only minor variations caused by solar radiation or gravitational flutter. But what they found next was something else entirely. The object's heliocentric course, its path around the Sun, had adjusted, not drastically, but deliberately. For weeks, 3i Atlas had followed a clean arc, consistent with an inbound interstellar body influenced by solar gravity and its previous momentum. Analysts had mapped its journey with precision, using inputs from deep space telescopes, Lagrange point monitors, and infrared satellites. Everything had fit, until now. At approximately 8 hours after the tail detachment event and the disappearance of spectral carbon lines, the object's trajectory began to diverge slightly from its predicted arc. Instead of continuing on its outbound slingshot path, it veered just enough to raise every eyebrow at NASA's Goddard Center and ESA's orbital mechanics desk. A shift of a fraction of a degree, but over astronomical distances, it meant something massive. It meant 3i Atlas was no longer simply coasting through space, it was adjusting. The path alteration wasn't chaotic or caused by an external force like a solar flare or impact. It was smooth, curved, as if guided by an internal mechanism that knew exactly where to place itself in the solar system. In response, orbital models had to be revised. Predictive simulations using the original vector began to fail. Legacy software that tracked comets had to be overridden by satellite defense-grade physics engines, usually reserved for near-Earth object avoidance programs. And once recalculated, the object's new trajectory told a chilling story. Instead of escaping the solar system, as expected, 3i Atlas's adjusted course now aligned with a much tighter, elliptical path, drawing it into a longer solar orbit. This meant it was no longer just a visitor, it was staying. What shocked many was the elegance of the maneuver. Comets that break apart or get pushed by outgassing typically veer erratically, shedding debris or entering rotational instability. But 3i Atlas maintained full cohesion, no fragmentation, no plume, just a clean pivot, like a glider catching a thermal current and adjusting its glide path with perfect control. This was not what interstellar debris does. Astronomers began comparing notes to see if there had ever been a documented case of a comet self-adjusting into a closed solar orbit after nearing perihelion. Nothing came close. The only precedents involved spacecraft, machines. Some hypothesized that the angular momentum change in Chapter 25 had been a prelude, a necessary calibration before executing the orbital curve. In that sense, the spin and the path weren't separate anomalies. They were part of a sequence, a coordinated series of moves, and here's where it got even more unnerving. The new trajectory positioned 3i Atlas to reapproach Earth's orbital plane, but from the opposite side of the Sun, not in a collision path, but in a mirrored alignment that would allow the object to track alongside Earth's orbit at a distant parallel. Some described it as a shadow arc, a sort of invisible twin path just far enough to remain undetectable to the naked eye, but close enough to stay connected. Why would an object, any object, do that? Was it stabilizing for observation, setting itself up for a return, or simply choosing a location from which to watch? Whatever the case, the change confirmed a truth that scientists had been whispering for days. 3i Atlas was no longer behaving like an object on a blind trajectory, it was behaving like something with awareness of position, orbital awareness. And the only things we've ever seen do that, carry guidance systems. This wasn't just a change in speed or spin, it was a decision, one made in silence but recorded in the mathematics of its path. And now, 3. Atlas was not leaving, it was settling in. In the aftermath of the orbital shift, attention turned once again to 3i Atlas's surface, or rather, what remained visible of it. High-resolution imaging had always been difficult due to the object's unpredictable light curve, but with the recent orientation change and its stable new arc, Earth-based and orbital telescopes were able to get the clearest sequence of frames ever recorded, and what they showed was unexpected. The surface of 3i Atlas was changing, visibly but subtly. Over a span of 10 hours, a pattern emerged. The object's rough, jagged topography, previously characterized by sharp albedo shifts, irregular edges, and broken protrusions, was now smoothing out. Craters, ridges, and chaotic markings that had once defined its rocky shell were beginning to fade. Not due to motion blur, not due to sensor noise. Frame after frame, confirmed across 4 independent observation platforms, showed the same outcome. The object was gradually developing a uniform texture, and it didn't make sense. Natural objects in space don't become smoother over time unless subjected to intense erosion, tidal flattening, or atmospheric re-entry. But 3i Atlas was in open space, far from planetary surfaces, experiencing no friction, no wind, no pressure. There were no impacts, no thermal flares, no collisions. Yet the transformation continued, relentlessly subtle, but undeniably visible. One by one, the contrast between bright and dark zones began to neutralize. Regions that had once reflected sunlight at high intensity now dimmed, while dull zones began to catch more light. The result was a uniform grey-white sheen, like powdered metal or finely polished stone. ESA researchers called it albedo convergence. NASA's imaging team simply labelled the frameset surface homogenization phase. The terminology didn't matter. The message was clear. The shell was becoming seamless. This observation came on the heels of the earlier revelation that carbon signatures had vanished from its spectrum. With the tail already ejected and the object's trajectory altered, it seemed that 3I Atlas was engaged in a full-body transition, one that erased all identifiable surface markers. But the question was, why? One theory proposed that the smoothing was the result of a self-healing material, similar to reactive polymers or nanoalloys developed on Earth that seal cracks under thermal or electrical stimulus. Another idea, more radical, suggested that the surface wasn't smoothing at all, but that it was becoming covered. That something, perhaps a fine particulate mist, a reflective shell, or even an electromagnetic layer, was wrapping around the object in waves, creating the appearance of smoothing, while in reality concealing the true surface beneath. This theory gained traction when infrared readings began to show an unusual shift: thermal flattening. Normally, rough objects radiate heat irregularly based on topography, but 3I Atlas's surface temperature began equalizing across all vectors, another sign that any internal variations were being masked. If this was a form of camouflage, it was working. Spectrometers began losing the ability to distinguish between mineral types. Reflectivity tests no longer showed directional variance. Even radar bounces returned with reduced scatter, as if the surface was absorbing and compressing signals into a narrow band. More simply put, we were losing the ability to see it. Avi Loeb was among the first to connect the dots. If this were a probe, he said quietly, this is what it would do before going silent. Because in the vacuum of space, visibility is vulnerability, and if 3I Atlas was preparing for something, observation, redirection, activation, or contact, it would first make itself invisible to noise. No flare, no flash, just a shell, becoming smooth enough to disappear into light itself. And so, the object that once erupted in colour, danced with jets, and carried a glowing tail across the stars, was now polishing itself into silence, or worse, preparing for the next move. Just as the surface of 3I Atlas was becoming unnervingly smooth and uniform, another unexpected development unfolded, one that directly contradicted everything scientists had observed in the previous hours. The backscatter light returned. For days, astronomers had noted an eerie decline in reflective signal returns from the object. Its increasingly polished shell had seemingly absorbed or deflected any meaningful light bounce, rendering traditional optical and radar observation almost useless. Instruments designed to measure reflectivity across multiple wavelengths began to register nearly flat responses, as if the object were deliberately cloaking its presence. But then, without any precursor or triggering event, that silence broke. A spike in backscattered light, sharp, clean, and coherent, flashed across instruments at ESA's optical ground station, followed moments later by near-identical returns from NASA's infrared and microwave observatories. Initially thought to be an error, the data was rerun across multiple calibration models. The result was the same. Light that had once vanished upon contact with the object was now bouncing back, and not randomly. It was directional. Unlike natural bodies, which scatter light unevenly depending on surface composition, rotation, and angle of incidence, the light from 3I Atlas returned in consistent arcs, centered around 2 points near its equatorial plane. This geometric symmetry caught the attention of physicists and optics experts alike. It wasn't just reflecting, it was signaling. Some called it a bloom, others labelled it a surface resonance. But the patterns in the returned signal were too clean, too deliberate. It looked like a calculated refractive response, as if the object had switched from concealment to visibility on its own terms. This begged a deeper question. If the object had chosen to reveal itself again, why now? And what had changed? Some theories centered around its new position in solar orbit. By settling into a mirrored trajectory opposite Earth, the object may have been attempting to create a kind of optical handshake, a calculated light return designed to be seen at a specific angle by a specific observer. Others speculated that the smoothing of the surface wasn't just about hiding, but about preparing for a reflective operation. Like a dish or panel, the smooth shell could now act as a controlled mirror, bouncing light not diffusely but intentionally towards sensors. This line of thinking gained traction when scientists reviewed older data from the object's initial inbound journey. Early on, 3I Atlas had exhibited flickering behaviour, short bursts of reflectivity, followed by sudden silences. Many had written this off as tumbling or jet interference, but now, in hindsight, it appeared to be part of a pattern, one that was repeating now, only with higher precision, and then came the next anomaly. The returning light began to polarize. Standard solar reflection does not exhibit significant polarization unless filtered through crystalline structures or engineered surfaces, yet 3I Atlas's backscatter signal began aligning along single-axis polarization bands, indicating that it wasn't just returning light, it was filtering it. To those in the optics field, this was no longer a passive surface. It was a designed interface. Avi Loeb once again voiced what many were thinking. When light returns from an object in this way, we're no longer just observing it, we're being observed back. The implications were immediate. Satellites shifted their tracking protocols. Deep space arrays began full spectrum monitoring, and for the first time since the object's tail detached, the possibility of two-way observation took center stage. It wasn't a burst, it wasn't a solar flare, it was a controlled reply, silent, invisible to most, but unmistakable to those who were watching closely. 3I Atlas had spent hours shedding its identity. Now it was sending something back, not a message, not a code, just light, refined, structured, and unmistakably intentional. And somewhere, from deep space, it was watching us watch it. It didn't happen with fanfare or emergency sirens. It happened with a quiet bulletin, slipped into the international data feed at just past 3 in the morning. The Minor Planet Center, the global clearinghouse for celestial object tracking, had issued an observation priority upgrade for 3I Atlas. This might sound procedural to the outside world, but to those familiar with the process, the message was clear. Something had changed, and the global astronomical community was now being told to watch closely. The designation moved 3I Atlas from a standard transient object, comets, asteroids, and interstellar passers-by, into a much narrower category of active monitoring targets. Only a handful of bodies are ever flagged this way. Most are near-Earth objects with potential impact vectors. Some are unclassified anomalies. A few, like Oumuamua before it, sit in a grey zone of unknown intent. But none of those ever received this kind of mid-orbit escalation. What triggered it was not just the backscatter light returning, nor the shift in heliocentric course. It was the combination, a series of escalating anomalies that painted the picture of something no longer inert, no longer random, and no longer easy to model. Within hours of the bulletin, observatories across the globe began redirecting telescope time to the object. Slots once reserved for deep field imaging or planetary studies were now overwritten. Even non-optical instruments, radio arrays, gamma sensors, LiDAR units were retasked. Why? Because the data was converging on a truth that few wanted to say out loud. 3I Atlas was behaving like an object under control. The center's internal notes, later leaked to several independent researchers, revealed the reasoning behind the upgrade. Among the factors cited were the controlled smoothing of its surface, the reappearance of polarized backscatter light, the intentional angular shift in orbit, the loss of volatile material without fragmentation, the synchronization with Earth's orbital plane on the far side of the Sun. And perhaps most chilling of all, there had been no sign of natural decay. Typically, cometary bodies degrade over time. Their surfaces crack, their cores vent, their trajectories jitter as they lose cohesion. But 3I Atlas was doing the opposite. It was becoming more coherent, more stable, more deliberate. By issuing an observation upgrade, the Minor Planet Center wasn't just asking astronomers to take better notes. It was implicitly warning that something more was unfolding, and the standard catalogue entries were no longer sufficient to capture its behaviour. In response, a dozen private space companies, many of them contracted with government agencies, were ordered to submit all unpublished observational data. The object's profile was uploaded to defence-grade modelling systems typically reserved for national security satellites and launch windows. But this wasn't about collision, it was about intention. 3I Atlas had crossed the threshold from being a foreign object in our system to becoming a known actor, a presence. The language in official reports began to shift. Terms like anomalous light behavior were replaced with directed reflectivity. The phrase orbital instability gave way to course correction. And most telling of all, for the first time, several agencies began referring to the object not as a comet or a rock, but as a body of interest. Not dangerous, not yet. But important enough to divert the full weight of Earth's scientific apparatus toward it. This wasn't surveillance, it was acknowledgement. Something had arrived. Something had changed. And now, with telescopes pivoting and models recalibrating, the world's scientists were no longer guessing. They were watching, closely, quietly. Because the object that had once roared into our system with a tale of fire and mass was now drifting silently in plain view, and rewriting the rules as it went. In the early hours following the Minor Planet Center's observation upgrade, something subtle but unsettling began to emerge from the radio data. It wasn't a flare. It wasn't a spike. It was a pattern. Buried within the low-frequency telemetry pulled from long-range radio arrays, specifically those located in Chile, Australia, and West Virginia, analysts began noticing a repeating pulse. Not one loud enough to trigger an alarm, and not structured like a transmission, but present, persistent, quietly repeating every 48 minutes. This wasn't a new frequency, nor an anomaly that had arrived with a burst. It was there in the background of existing data, going back at least 2 days. Only now, with enhanced observation protocols, were the timestamps and amplitude graphs clean enough to isolate the repetition. Every cycle matched the last. A soft rise in signal strength, a sharp plateau lasting 4 seconds, and then a decay, resetting the loop. It didn't match solar wind harmonics. It didn't align with the pulse cycles of known stars. It wasn't echo from Earth-based infrastructure. It was originating from the vicinity of 3I Atlas. What made this discovery even more perplexing was the frequency band itself. It existed in the very low end of the time domain, barely above background noise, where only a handful of natural processes emit regular signals. But this one was too clean, too consistent, too intentional. The first to raise the alarm was an independent researcher operating out of New Zealand, who published an unlisted report on a known astronomy forum. Within hours, the post was flagged, locked, and pulled, but not before several researchers across Europe and North America verified the data for themselves. The consensus was chilling. This was not random. This was not thermal noise. This was a clocked pattern, as if something was measuring time. Speculation, predictably, erupted. Some suggested the pulse might be a kind of internal calibration from within 3I Atlas, a feedback loop akin to what satellites and spacecraft emit as they cycle through systems checks. Others wondered if it was the product of a rotating mechanism or oscillation within the object itself, but the data did not support those ideas. There was no accompanying rotation signal, no magnetic variance, no mass shift to correlate with a wobble or spin. The object wasn't rotating at a rate that would explain a signal every 48 minutes. It was, instead, emitting a pure signal, tied to nothing but time. The implications became heavier the longer analysts stared at the return curves. If this was not the byproduct of decay or motion, then it was purposeful. It might not be a message, but it might be a heartbeat, a baseline signal, a marker of uptime, or perhaps a trigger. Because at the exact midpoint of each 48-minute cycle, astronomers began to notice a faint polarization in the returning light, too brief to measure conclusively, but present enough to make some ask. Is this object syncing itself to something? And if it is, what is it syncing with? The James Webb Space Telescope was briefly repositioned to capture reflected infrared during the signal's peak cycle. Nothing anomalous was seen. But the timing itself, the regularity, the silence, the precision, had now placed 3I Atlas into a category no scientist was eager to define. An engineered rhythm, not an SOS, not a language, but a cadence, one that didn't change, one that ignored the sun, the planets, the magnetic fields, and instead simply counted time in silence. 48 minutes, every time, no variance, no modulation. Just a low, echoing whisper in the noise floor of the cosmos. And it was still going. Whatever 3I Atlas had become, it was awake. While most eyes remained locked on the deep space behavior of 3I Atlas, a shift occurred much closer to home. Subtle at first, but rapidly becoming impossible to ignore. At approximately 2:40 in the morning UTC, a wave of unexpected auroral activity was detected over the northern latitudes of Canada, Scandinavia, and parts of eastern Russia. The event lasted just over 11 minutes, but what made it remarkable wasn't its brightness or reach, it was timing. The aurora spike coincided perfectly with one of the 48-minute signal pulses emerging from 3I Atlas. To observers on the ground, it appeared as a thin, rapidly intensifying band of green and red light, followed by a quick fade. It was too short for most commercial aurora tours to capture, but satellite instruments caught the event in full detail. What puzzled experts wasn't just the brevity of the display, but the lack of a corresponding solar trigger. Typically, auroras are caused by solar wind particles slamming into Earth's magnetic field, especially after coronal mass ejections. Yet on this night the sun had been calm. No flares, no CMEs, no spikes in geomagnetic indices. The space weather forecast showed nothing unusual. The solar wind was steady. Proton flux was low. There should have been no auroras at all, and yet there they were. A flash of energy from above, then gone. Space weather monitoring stations began pulling logs, trying to trace the origin of the brief magnetic fluctuation that preceded the aurora. The disturbance didn't fit the profile of solar interference. Instead, it came in a tight burst, like a pinprick to the magnetosphere, followed by a rapid dissipation. The source direction was logged as outbound, coming from well beyond lunar orbit, and the trajectory lined up precisely with 3I Atlas's path behind the Sun. For a few hours this was considered a coincidence. Then came the second auroral pulse. Roughly 48 minutes later, another brief arc of colour flared in the same high-latitude regions. This time it was even shorter, barely 6 minutes. Still no solar activity, still no proton events, just a magnetic twitch, a surge in ionospheric activity, and then light dancing silently across the sky. At this point, the evidence was harder to ignore. An object millions of miles away was having a measurable effect on Earth's magnetic field. Twice. Scientists at NOAA and ESA's Space Weather Prediction Center issued internal queries. Could this be a high-frequency energy pulse? Could it be a byproduct of gravitational resonance? The model said no. Earth's position wasn't aligned for any known magnetic interaction. There was no predicted resonance window, no current sheet crossing. The magnetosphere should have been still. And yet the lights danced again. This left one unnerving theory. What if the object was probing? Not attacking, not signalling, but nudging, just enough to test the envelope of Earth's magnetic shell, like sonar, like echolocation, like something trying to learn the shape of what it was approaching. It wasn't a destructive act. There was no damage. Satellites remained online. Radio transmissions were unaffected. But the precision of the auroral timing and the lack of any natural precursor set off silent alarms in defense and research. Circles alike. Backscatter polarization from 3I Atlas also spiked during the same window, suggesting that the object itself may have anticipated the auroral response, or even caused it. And so, for just a few minutes, the skies above Earth glowed. Without a flare, without warning, without the sun. Something out there had reached in, not loudly, not obviously, just long enough to say, "I see you." And then, as suddenly as it began, the colour vanished from the sky, leaving only quiet magnetic records, puzzled scientists, and a growing feeling that Earth had just been gently tapped from afar. It wasn't the most dramatic event. There was no burst of light, no electromagnetic surge, no auroral trail, and yet, among the world's orbital observatories, this was one of the most chilling developments yet. Roughly 3 hours after the second auroral flash faded from Earth's polar skies, the Solar Dynamics Observatory reported a distinct, unambiguous reorientation of the jet stream being emitted from 3I Atlas. Previously, the object had been releasing asymmetrical jets, short bursts of ionized material, ejected at irregular angles, sometimes spinning off from the tail or curving away from the sun. These jets had been erratic, shifting, rotating, natural, but now one of them had gone dead straight, locked into position, and it was pointed directly along the Earth-Sun line. Not near it, not vaguely in our orbital quadrant, perfectly aligned. This wasn't easy to detect. The initial alert came not from a major agency. but from a high-resolution amateur observatory in Argentina that noticed a sustained thrust feature in stacked exposures. When overlaid with ephemeris data, the conclusion was inescapable. The jet's projection traced a straight path through the solar ecliptic, matching Earth's current orbital vector with near-zero angular drift. ESA's Solar and Heliospheric Observatory quickly confirmed the finding. Their coronagraphic images revealed the jet cutting cleanly through the inner solar system, not spreading, not diffusing, holding. For many researchers, this changed the tone entirely, because this wasn't just a jet. It was a directional act, a jet of material, possibly plasma, possibly dust, possibly something unknown, being emitted deliberately in one direction toward a moving target, toward Earth, through the sun's gravitational lensing path. This was something comets simply don't do. They vent, they react to sunlight, they break apart, they don't target. Speculation ignited again. Some theorized it could be an alignment fluke, a byproduct of gravitational rotation. But simulations failed to support that. The jet held too precisely. Its stabilization was too clean, too long, too efficient. Others feared something more, that 3i Atlas wasn't just awake, it was watching, not with eyes, but with orientation, with geometry, with a level of intentional positioning that bordered on mechanical. Avi Loeb, contacted by multiple research groups for interpretation, reportedly offered a chilling analysis. This isn't a random alignment, this is choreography. The implications were staggering. If 3i Atlas had real-time awareness of the Earth-Sun line, it meant it had the ability to process positional vectors in three-dimensional heliocentric space. That requires feedback, sensors, a navigation model, or something beyond what current science attributes to interstellar objects. Furthermore, the jet showed no variance over the next two observation cycles. Even as the Earth continued along its orbital path, the emission held its angle, suggesting that either 3i Atlas had updated its vector in advance, or that it was actively tracking Earth's position in real time. But there was one more twist. When modelling the jet's reach using solar wind data, analysts discovered that the stream would not physically contact Earth. It would pass within millions of kilometres, but its orientation alone was enough to act as a symbol, a marker, not a weapon, not communication, a gesture, a single, sustained, unchanging line of energy drawn between itself, the sun, and us. As if to say, I know where you are, I've chosen to look there. And yet, despite the intensity of the alignment, there was no radiation spike, no particle storm, no increase in space weather. The jet itself, while visible in high-contrast imagery, appeared to carry minimal mass. This was not force, this was posture, and in the silence of deep space, where distance usually protects us from intent, this deliberate line felt more intimate than anything yet recorded. 3i Atlas wasn't speaking, it was pointing, and Earth was now directly in the line of sight. It began as a faint anomaly, just a flicker in the outer limb of the sun's profile, captured during a routine scan by the Solar Dynamics Observatory. At first, it looked like a brief drop in ultraviolet intensity along the southeastern quadrant of the solar corona. Nothing dramatic, no flares, no spots, no bursts, but it didn't fade. Instead, the numbers kept drifting downward, not sharply, but consistently, and only in one isolated sector, roughly 6 degrees wide, positioned precisely in the direction where 3i Atlas's aligned jet had been aimed the night before. What made this finding so bizarre wasn't just that the sun's corona was changing, but how it was changing. The solar corona, the outermost layer of the sun's atmosphere, is one of the most extreme environments in the solar system. It burns at temperatures reaching over 1 million degrees, seething with plasma and driven by magnetic chaos. It's unpredictable, wild, and violent. Except now, it was cooling down, gradually and locally, like something had gently pressed on a pressure valve and released heat, not by expelling it, but by suppressing it. NASA's heliophysics teams initially suspected a sensor calibration drift. Instruments age, after all, but cross-referenced data from ESA's solar orbiter told the same story, the same region, the same drop, and the same pattern of suppression, beginning shortly after the Earth-Sun line jet alignment from 3i Atlas. Temperature estimates fell below typical coronal values by nearly 7% in that pocket, and the cooling area held steady, even as the rest of the sun continued its chaotic flares and ejections. The big question wasn't how much, but why. What could cause a precise segment of the sun's corona, measured in real time from multiple orbital perspectives, to subtly shift out of thermal equilibrium? And more importantly, why that segment? Because when plotted geometrically, the affected slice of the corona matched the projected path of 3I Atlas's jet vector, creating a perfect linear overlay between object, solar jet, and now, solar response. This sent a chill through the astrophysical community. Was 3I Atlas merely reflecting some kind of exotic particle? Could its jet be bending magnetics, or was it draining something? Some theorized a process similar to magnetic reconnection, but on an interstellar scale. Others quietly explored even stranger ideas, the notion that the object might be drawing or redirecting solar energy through gravitational lensing, or even that it had triggered a localized magnetic dampening. But one thing was clear: the sun had never cooled like this. Not in this way, not in this shape, not in this line. It wasn't an explosion, it wasn't a flare, it was the absence of both. Silence, inside the most violent place in the solar system, and the phenomenon only grew more eerie. When observatories used coronagraph imaging to isolate the cooler zone, they noticed that light scattering within the region had dropped, not just in heat, but in turbulence. Solar wind streams appeared smoother in that sector, less chaotic, as if something were reducing the plasma's random motion. Like a hand smoothing the surface of boiling water. This wasn't just about cooling, this was about control. And once again, the vector pointed back to 3I Atlas. Avi Loeb, in a closed-door conference, is said to have summarized it in one line. Whatever that object is, it's not afraid of the sun, it's shaping it. Whether that shaping was deliberate or incidental remained unclear, but from that moment on, one truth hovered behind every whispered conversation, every observatory alert, every recalibrated sensor. The sun had blinked. Not because of itself, but because something else was in the room, and Earth was next in line. It was just after sunrise across Europe when the data feeds fell still. No more spectral surges, no more reoriented jets, no new pulses, no auroral flickers, no magnetic anomalies, just silence. The sky above Earth looked the same, but the rhythm was gone. For the past 72 hours, 3I Atlas had dominated the attention of every major observatory in the Northern Hemisphere. Its behavior had escalated step by step, moving from dramatic tail loss to directed emissions, strange interactions with the sun, and alignment patterns that defied natural precedent. Each new event hinted at something bigger, a rising pattern, a building crescendo. Analysts whispered of intentionality, of choreography, of something we were meant to see, and then, without warning, it all went still. At first, researchers thought the sensors had glitched, a dead telemetry packet, a momentary blackout. But redundant systems from NASA, ESA, and private space agencies confirmed the same thing. 3I Atlas was no longer active. Its aligned jet, gone. Its pulses, silent. Its brightness, dimmed to background levels. Even the strange cooling arc in the solar corona. Already warming back up. The object hadn't vanished. It was still there, moving along its projected heliocentric path, slowly drifting into its outbound phase. But everything that had made it strange, intense, alive, had faded. There were no energy spikes, no decay signatures, no thermal bursts. It hadn't exploded. It hadn't disintegrated. It had simply stopped. And that, in many ways, was more unsettling than any burst or break. Because if 3I Atlas had been following a sequence, a pattern of behavior that escalated in complexity and intensity over days, and if that pattern had been oriented in Earth's direction, then why stop? Why stop now? Some analysts believed it had completed its objective, that it had watched, scanned, measured, that it had finished whatever interaction it came here for, that Earth, the Sun, and the orbital geometry between them had been part of a brief, intentional observation window. Others suggested the object had entered a hibernation phase, that what we had witnessed wasn't an end, but a pause, a temporary cease in visible activity before it transitioned to the next leg of its journey, toward the outer solar system or beyond. A small group feared something darker, that it was now waiting. Having sent its signals, drawn its lines, and triggered reactions, it was now holding position, not out of exhaustion, but by design. Regardless of theory, what lingered was the emotional shift. For days, the global space community had operated in a heightened state of attention. New alerts every hour, constant cross-checking between observatories, a rising pulse behind every headline. And now there was only the absence of signal, an eerie void where there had been activity, like waking up to realize the sound that had been keeping you company all night has stopped, without you noticing when. Even amateur astronomers could sense it. Online communities that had been buzzing with live tracking data began to quiet. Enthusiasm faded. Observers found nothing new to point their scopes at. No changing brightness, no new angles, just a dim, drifting object sliding silently away from the sun. NASA removed the priority status from its tracking bulletins. ESA updated its threat index to neutral. The Minor Planet Center logged its position and moved on. But among those who had followed 3I Atlas closely, those who had seen the strange alignment, the cooling corona, the directed jets, the magnetic taps, there was no relief. Just a single question that wouldn't leave. Did it finish watching, or is it just waiting? Because whatever intelligence, natural or not, had animated the comet's strange behavior had gone quiet, and in that silence, Earth was left with only its reflection. No answers, no response, just the feeling that, for a moment, it had been seen, and then it stopped.